Okay.
Yeah. So a short bio about Luciano Agustini. Luciano Agustini received his MS and PhD degree in computer science from Federal University of Rio Grande, Brazil in 2002 and 2007 respectively. Since 2002, he has been a professor with Federal University of Pelotas, Brazil, where he has leads the Video Technology Research Group and is advisor at the Master and Doctoral in Computer Science course. He is a Brazilian distinguished researcher through a CNPq PQID grant, 1D grant. He had been UPPL Executive Vice President for Research and Graduate Studies from 2013 to 17. He has more than 300 published papers in respected international journal and conferences. His research interest includes 2D, 3D, and omnidirectional video coding, point clouds, light fields, algorithmic optimization, and dedicated hardware design. He is an associated editor of IEEE Transaction on Circuits and System for Video Technology and for IEEE Open Journal of Circuits and System. He is a senior member of IEEE and SCM and a member of SBC and SB Micro Brazilian Society. He is also a member of IEEE SPS, CS and CAS Society and CS. He is a member of MSA VSP Technical Committee. So on behalf of all our technical committee and program committee, I welcome you again, sir. So we will happy to you got you here. Okay, thank you. Welcome again, sir. Over to you, sir. You can start.
Thank you, Professor Deepak. I will share my screen now.
Yeah, you can say.
Okay. It's okay?
Yeah, it's okay.
Okay. Let's start here. Well, it's my pleasure to be here to you tonight in Brazil and this afternoon in India. I'm professor from Federal University of Pelotas in South Brazil, and I will talk a little bit to you today about a theme that is very interesting for us, and we are researching on, which is the video coding and the versatile video coding standard. Let's go. I am here in the South Brazil, almost in Uruguay, and my university, the Federal University of Pelotas, and we are working inside the Center of the Technological Development, where we have our PhD and master courses, and also our undergraduate courses. And the research group where I'm working with this team is the Video Technology Research Group. Well, here is the city, and the city is near to a big lagoon called Duck Lagoon, and the university is spread around many buildings around the city. You can see here some historical buildings also, and this one is the headquarters of the university, where is the computation and I work. The computation is located, is near to a big river also in our city, São Gonçalo River. This is the professors of the Video Technology Research Group. We have 5 professors nowadays, and 23 PhD students, 8 master students, and 14 undergraduate students. Here we have some talks that we are working with. We work with a lot of types of visual signal, from still images and 2D and 3D videos, 360 videos, point clouds, light fields, and basically we have 2 main approaches or 2 main interests. The first one is related to algorithm design, where we try to develop new algorithms and to process this type of videos, of visual systems, and we try also to reduce the complexity of the algorithms defined for these standards, like the VVC that we will talk a little bit today. And also we have another work related to system level solutions where we try to implement in hardware with dedicated hardware or some embedded systems, efficient solutions to handle these very complex algorithms used mainly to compress this type of media. Well, here I have a brief summary of my presentation. First, I will talk a little bit about motivational analysis to show you why it's really important to work with video coding. Then I will talk a little bit, I will present some basic concepts related to this area to better understand what's happening. And then I will present the VVC standards, the versatile video coding, which is the state-of-the-art video coding standard from the two main international organizations for standardizations, ISO and ITUT. Then some trends and conclusions. Well, a forecast for from Cisco tells us that in this year there is a forecast that is almost 61 exabytes will be over the internet, will be video per month. There is a lot of content over the internet nowadays related to video, and this traffic is estimated to be almost 8% of the global internet traffic. I want to know that this video is really very important nowadays. And the forecasts also show to us that the video content over the internet will grow 55% from 2017 to 2022. Then there is an increased demand for this type of information. I will show you at the end of this presentation why, but you can imagine that we are using more videos and with more resolutions, and we try to have more quality and so on. And also videos, it is very interesting. Also videos will represent 79% of mobile data traffic in 2022. This means that besides the importance for the internet global traffic, but also the mobile traffic, typically using smartphones, for example, battery-powered devices, the videos are also very important in this type of scenario. And by 2023, 66% of connected TV sets will be 4K or larger. Then some aspects important to show, and only to present some size of this problem related to video, or the size of our motivation to work with video. If you're considering a video with 24 bits per pixel, which is a very common way of represent a video, then we have 3 bytes per pixel, and a full high definition resolution like this one, and 30 frames per second. Considering a typical movie with 2 hours, how many bytes we need to represent this video without any compression? You can see it's easy to get this number. First, you need to know how many pixels you have in the horizontal in each frame, then multiply by the vertical pixels. Then we know now how many pixels you have per frame. Since you have 3 bytes per pixel, you need to multiply by 3. Now you have the number of bytes inside a frame. If you multiply by 30, then you have the number of bytes required to represent 1 second of this video. And if you multiply by 2 hours, then we get the value of 1.3 terabytes to represent only 1 movie. Then compression was, and this still is essential to spread digital videos. Naturally, 1.3 terabytes is completely impossible to consider to process this type of information. Well, but nowadays you can reach impressive compression rates as you know, with minor quality degradations. For example, Netflix typically use 3 gigabytes to encode that videos that I presented before with 1.3 terabytes. This means that the compression rate they are using is something like that 450 by 1. There is an impressive compression in this scenario, and then I'll show a little bit how this is possible. But you are still need more efficient solutions than this market, and the research for this type of solutions is still growing a lot. Another challenge in this field is that, okay, we have very efficient solutions to compress the videos, but the solutions requires a very high computational effort. This is a big problem because this implies in high costs of the device, since we need more computational power, but also we have another problem related to energy and power consumption. This is mainly important for battery powered device. And also the time to encode and decode videos is a problem in the scenario. We have a lot of applications like this one that we are using today. The video must be compressed in this side and decompressed in your side to see my face and the slides. And this must be very fast. Well, to surpass these challenges, basically we have two main approaches. The first one is to develop even more efficient algorithms to compress the videos, able to reach as smaller as possible video files. This means as higher as possible compression, with as higher as possible video quality. This relation between compression and quality is called coding efficiency. Okay, then we try to increase as much as possible the coding efficiency. But to handle with the high complexity of this process, then we also need efficient systems able to process these algorithms in real time and with as smaller as possible energy and power consumption. Okay, then we have two types of solutions typically explored in the works nowadays. Here, I have only one example to show you that we need all systems, not only algorithms running in general processors. The current general processors, the embedded processors, and the GPUs, and many other hardwares have inside these hardwares some specific solution with hardware dedicated to decode and encode video coding, video information. Okay, then in this case you have this GPU that have a specific processor inside the GPU developed with dedicated hardware optimized to decode video. And here we have a lot of standards which are supported by this processor to decode, and we have two formats here used to encode. Only to perceive that it's completely impossible to have a cell phone nowadays without some dedicated hardware able to process videos to allow us to have our applications running. Well, some basic concepts now to understand the main concepts related to video coding. Well, a digital video is a sequence of still images which are called frames. Here we have an example of these frames. Here, side by side, only to see. Well, as you can see here, if you have discrete images, we need to have some frequency of capture and reproduction to allow our human visual systems to perceive the movements. Then we need to have at least 24 to 60 frames per second to allow this the perception of the movement in a scene. Okay. Each frame is composed by 3 bidimensional matrix with discrete points called samples. Each point inside this matrix is a sample, and a group of samples in the same position in the 3 matrix is called pixel. Okay. Well, the way how the color is represented is called color space, and the most famous color space is the RGB, the red and blue. But the video coding community typically use another format called UI CBCR. In this case, we are completely separating the brightness of the information, the luminance of the information, the Y channel, from the color information. And this is very useful, as I will show to you in the next slides. Well, other important things is that the frame is not processed as a whole in only one step. We need to partition the frame in smaller blocks, and current encoders allow the use of different block size. Then we need to evaluate which combinations of box size is the best one to encode that frame region. Okay, and naturally this is not easy to do, and we have a complex structure to represent this partition, typically using trees. I'll show an example, the example of the VVC in the next slides. And here we can see one example of one encoder where we have a lot of block sizes allowed, and the more homogeneous regions tends to be encoded with a larger block size, because for each block we have also lateral information indicating which type of block is that, which is the size, which is the motion vector. I will talk about motion vector in the next slides also. And there is some lateral information. Then as bigger is the block size, better is, because you have less lateral information for the same area. Okay. If we consider to use some more if you have a more detailed region inside a frame, then in this case typically we will use smaller block size. Okay, because in this case we need more details, and these details could be lost if you use a big block size. Then you have a complex process to decide when each block size will be used. Well, and how the very high compression rates are possible? Basically, we have 3 strategies. The first one is exploring data redundancies, which are typical in digital videos. We also can explore the human visual system, and you can explore the probability of symbols occurrence. Okay. Well, the first strategy, which is the exploring the data redundancies, the first redundancy you have inside a digital video is the temporal redundancies. The neighbor frames are very similar, as I showed to you in these examples here. There is a lot of information which are very, very similar. Then we can avoid to represent the same information many times. Okay, for example, here we have exactly the same information in this part of the video, here also, and then we have an operations used to explore the data, this type of data redundancies, which is called inter-frame predictions, the prediction between frames. And we have 2 main operations here. For example, if this frame is being processed, then we get one block of this frame, and we will try to find inside the previous frames, the previous processed frames, the best match, the block which is most similar with this one that I'm processing here. Then there is a process to do that, to find. We define how many frames we can search, which is the area inside each frame that we can search, and so on. But this process is called motion estimation of the movement. And the next is the second operation is the motion compensation. Then in this case, we get all the predictions because the original frame is different from the predicted frame, or the predicted block. Then the predicted block must be subtracted from the original one to guarantee that this difference will also be considered during the.
Sir, your slides are not changing.
I'm sorry?
Your slides are not changing. PPT is not changing. It's still in the first slide.
Sorry, one moment. I have a problem here. Oops. The slide is okay now?
Yeah, it's okay. It's okay now. Yeah.
I'll try again here. It's okay?
Now it's not changing. It's still in basic concept slide.
I don't know what's happened.
So can you just make a full screen, sir, once?
I don't know what I can do in this case.
Yeah, now it's changing. Basic concepts.
Yeah, because here I'm not presenting the PowerPoint.
Okay. Okay.
There is no, the animation is not working. I'll try again.
Okay. Yeah, you can stop share once again and again reshare once.
Okay, but I will show only to finish this explanation. Then we have here. Well, I will stop sharing and then I turn. Sorry.
No.
Let's go. Let's try present again. There is some animations. I don't know. Maybe this is a problem. It's working?
Yeah, no, sir. Still, it's on the same slide. Basic concepts.
Don't know. I don't know what's happening. I'll try to present in this mode, but it's very bad. Well, only here to finish this explanation. At least, I'm sorry for the problem. Then we have the motion estimation, which when we find for each block inside the current frame, the most similar block inside the reference frames. This is done by the motion estimation, and the motion estimation, when we will find this position, we identify this position using the motion vector to identify which block inside the other frame I will use to represent the current block. And the motion compensation, only get this block using the motion vector to subtract this block from the original one, since you have a difference between these two blocks. The prediction is not perfect, and this difference must be considered also. I'll try to present the next slide with the intra-frame prediction. I don't know if now the animations will run correctly. Are you seeing the special redundancies now or not?
It's still in basic concepts.
Basic concepts only, but it's crazy. I don't know what.
Can you just, sir, once again stop the meeting again? Can you restart?
I don't know what has happened. I'll try.
Okay, so you can leave the meeting once or again join the meeting. Then it may work.
Okay, I will leave the session. Okay, one moment.
I made you post, sir. Can you start?
Okay.
Sir.
Okay, no, it's okay. Thank you. I will try, and I'm sorry for these problems, but I don't know exactly what is happening. Okay, I'm start from here from basic concepts. Are you seeing part 1 basic concepts? Yeah.
Yeah. We can see basic concepts.
And now we change.
Now it is still in part 1, basic 1 concept, the title slide.
You can see now the picture.
No, sir. Still we not able to see. Then next. Yeah.
Now I can see the 6 pictures, not or not.
Yeah, no, sir. We are not able to see.
I'm sorry, I cannot understand.
No, we are still able to see the basic concept slide.
The first one, which is part 1.
Yeah, part 1, basic concepts.
I don't know what's happening. I really don't know. I'm seeing here, but I don't know. I will try to convert as a
Yeah,
PDF.
now it is showing basic concept 6 digital video sequence.
Okay.
Yeah, now it is changing now.
But okay, okay. I will try to do that using here with off presentations. It's not the best way to do, but because I have some animations. Okay, you can see here basic concepts. It's changing now.
Yeah, it's changing. It's changing.
I'm really sorry for this problem. I don't know exactly what is happening. But in this case, I will lose some of my animations, but I will try to present as better as I can. Okay. Here we have the 6 frames of one sequence. Then we can see here that there is a lot of similarities inside these frames. And here I was talking about the number of matrices of color representations, and I said that we have in video coding typically one matrix of Y, luminance or bridginess of the images, and the other 2 related to the color. Here I was talking about the partitioning, where I tell you that the big blocks typically are used for homogeneous regions and the smaller ones for the detailed regions. I talk about the 3 strategies: data redundancies, human visual systems behavior, probability of symbols occurrence, and so on. And in this point, I was talking about the motion estimation and motion compensation. Okay. The other way to explore data redundancies inside the digital video is to explore spatial redundancies inside the same frame. The neighbor samples tends to be very similar, and to have a lot of regions inside a frame. In this case, for example, that the samples are exactly the same. And then we can explore also this information to remove the redundancy and to maintain only the information that which is really important. And the operations that explore this type of data redundancies inside the encoder is called intra-frame prediction, a prediction inside the frame. Well, now the second strategy is exploring the human visual system behavior. In this case, we have some alternatives to explore our visual system. The first one is that our visual system is is less sensitive to color information than to brightness information. Then we can represent the Y information, the luminance information, the brightness information using the complete number of samples, but we can reduce the samples that we are using to represent the color, which is called color subsampling. In this example, the white circles here are the luminance information, and the light gray and dark gray here are CB and CR samples. Then in this case, we have only one CB and one CR samples associated to 4 luminance samples. Using this solution, we can almost have some almost imperceptible quality degradation, and we have a lot of compressions. You can have a 50% of the file size only reduction only using this type of strategy. But this is a lossy operation. Then when we discard the chrominance samples, we cannot recover the samples. Okay. The other way to explore the human visual system is to explore the observation that our visual system is less sensitive to high frequencies. Okay, then we can transform the visual information from spatial domain to the transform domain to DCT, for example, and then in this domain you can remove or attenuate those frequencies that are less important for our visual system. This is done through the quantization step. And then in this case, typically the quantization step will generate a sparse matrix with a lot of zeros. And the operation here typically is integer division. Then we have a lot of losses here. This is also a lossy process. Why? Because an integer division, then when we multiply 0 by the number that we have, we can have 0 as an answer. Then we cannot have another, again, at the same matrix. But this is also very interesting because you can get a very high compression efficiency using this type of strategy. And the quantization is very, very important inside the video encoder, because the quantization step is the model, the step of encoding that defines that relation that I said before to you, the coding efficiency. And we can have here, a quantization parameter which tell to the encoder how much compression we want to do. And then as higher is this parameter, as higher is the number of zeros in this matrix, this output matrix, and then we can have more compression. But in this case, we have more losses also, and then quality degradation. Then we have to work carefully here to get the best QP for each type of application. Okay. But at this point, we don't have yet the compression. The compression will be in the next step. I'll talk a little bit later to you. The last strategy to explore the human visual system behavior is the application of some filters to remove some artifacts generated by the encoding process. As I said before, we process blocks independently. Then it's this type of problem is typical in imaging, which is block effect, and also the quantization process that typically removes the highest frequencies will generate some problems like these ones in images, or these ones that are typically caused by the quantization. Then we can apply some filters to improve the visual quality of the information, but also we improve the reference that we are using to encode the next blocks. And since we are improving the reference, we also are improving the final compression efficiency. Okay. Well, finally, we can explore the third opportunity is to explore the probability of Simon's occurrence. Then in this case, you get typically this matrix from the quantization, and then we can encode using a variable length encoding strategy, which use a very low number of bits to represent the symbols that are more probable to occur with a very high compression efficiency. This operation is called entropy encoder or entropy coder. Typically, the current encoders, standards, and so on, use arithmetic coding. Okay, it's a type of encode to do this type of things. And then in this case, the entropy coder is really very efficient to encode the quantization outputs. Okay. When we group all these tools, we have the complete encoder, which is called okay, which we call hybrid encoder. Hybrid because are mixing all these solutions together. The first step is the prediction step, where you have the interframe predictions with motion estimation and motion compensation that use the current frame, the blocks inside the current frames, and also the reference frames. And you have the interframe prediction that use only the samples inside the current frame. Okay, then we did the prediction, one or one, the interframes or the interframes, and then the difference between the prediction and the original block, which is called the residues, are then transformed and quantized, and then the entropy coding is applied. But we need to have exactly the same reference inside the encoder and inside the decoder. Okay, since the quantization is a lossy operation, we need to guarantee that we have the same reference, that we are considering the same losses in both sides. Then the current frame is not used as reference frame for the next to process the next frame. At least this inverse operation of quantization and transforms, which is typically done inside the decoder, is applied inside the encoder also and added to the prediction, and then the filters are applied and only to generate the reference. Okay, then the new reference, this current frame original is the same current frame here, but now reconstructed. This means with the losses caused by the quantization process. And then this frame will be used as a reference for to encode the next frame. Okay. Well, I'll start talk about the part 2, the versatile video coding. I hope that you see correctly now. Well, here we have a timeline of the video encoders. The first standard was launched in 1988, the MPEG-1. Then we have the MPEG-2 in 1994. There's a lot of success of the standard. We have the AISP'22 in 2003, and this is still the most used encoders nowadays. In 2030, we have the HVC, which is the predecessor of the VVC, and in 2020, the VVC was launched. We also have some important development here, a parallel development from some very important companies, considering Google and many others, that try to have their own encoder free of royalties. This is the main idea. And then the VP line of encoders from Google was grouped with Dalan, Tor from Cisco and Mozilla, and with many other contributors to generate the AV1, which is also a very important encoder nowadays. Well, here we have a graph considering the compression efficiency, the coding efficiency, and the time, considering the different encoders. And now we have here the VVC and the previous standards of the ISO and ITUT, and these standards were the most important of their generation, the most used, the leading of the market. Okay. Well, VVC is the state of the art in the series of ITUT and the ISO standards, and the final standard was defined in 2020. And the main goal was to increase the encoding efficiency in 50% when compared to the predecessor of the HVC. All these encoders have some reference software, which is a proof of concept of the encoder to try to solution and so on, which is called in this case VVC test model VTM. It is freely downloadable in the site. Okay, and can get the encoder and the decoder in this site. The main idea of the VVC was to improve the existing service and also to enable new services. Then the idea was to support high quality and 4K video streaming, for example, improving the decoding efficiency, improve the 360 video and virtual reality streaming, improve telepresence and screen sharing, and also enabling new services like 8K with HDR, high definition range. Okay, also low latency for cloud gaming, immersive and telepresence, and IoT and automotive. Then the idea is to have a very flexible standard, and the name versatile is an idea of this main goals of the new standard. The VVC partition structure is the first division is called coding to units. Then this is squared blocks can have size from 32 by 32 to 128 to 128 of luminance samples associated with the prominence samples, and depending on the color subsampling, we have different size of prominence samples. And now you have bigger CTUs if compared with ADVC, since now you have support, you want to support efficiently also higher resolutions. Okay, each CTU is partitioned in a high flexible structure called quad tree with nested multi-type tree, PTMT. Okay, I'll talk a little bit this tree in the next slide. And each leaf of this tree is called coding unit. Then the prediction, the transforms, the entropy coding will be applied over coding units. Okay. The coding units can vary from the biggest size of the CTU to the 4x4. Okay, for luminance samples. And when we are encoding the frame using intra-prediction, you can have an independent tree for chrominance samples, okay? But only when we are using intra-prediction. The inter-prediction use the same tree for luminance and chrominance. The VVC, the partition allowed by this tree are three: quaternary, binary, and ternary. And this means that we can have this type of divisions and can divide the block in 4 squared block with equal size, or 2 horizontal or vertical blocks, or 3 horizontal or vertical blocks using this type of partition, which is not exactly balanced. But we can first use only a quaternary partitioning, which is a quad tree, is applied, and when we have a leaf of the quad tree, then we can apply the multiple tree, which is now available us to use binary and ternary partitions. Okay, we cannot use again the quaternary partition if you have some type of division of that. The reason is a little bit obvious, because you don't have squared blocks in this situation. Well, here we have an example of this partition. The bigger the sky here, which is a very homogeneous regions, are using bigger CTUs, and the detailed regions here are using smaller block sizes, smaller CTUs. And only to show one example here, we have this CTU is first divided into 4 blocks, squared blocks. This block here is again divided in 4 blocks, and this block is divided again in 2 blocks. Then a binary partition here is done, and then a ternary partition is done here. Then we have 1, 2, 3, 4 divisions to generate these leaves. Okay, in this example. Well, And now I'll talk a little bit about the tools related to the versatile video coding, considering the main operations that I tell before. The interprediction is working with the same seal size from the HVC, but the main difference here is that the HVC considered only squared blocks and now can use also rectangular blocks. Then now you have 17 seal size allowed, where the HVC supports only 5. And we have planar and DC modes, as in the HVC, which use only the information inside the frame and not, to generate the prediction, does not use information from the neighbor samples. But we also have angular modes, and VVC supports 65 angular modes, where HVC supports only 33, which are angular modes. Here we have an example. Angular modes will use one line of samples above the block and one column of samples at the left of the block. And then with these samples from neighbor blocks, using these samples, you can interpolate the samples to generate a prediction considering one of these 65 different directions. And then we can have a prediction using the information of neighbor samples. Okay, you need to try these predictions to define which is the best one. Well, we also have one situations called multiple reference lines, when in some specific case you can use more than one line and one column. In this case, you can use 2, 3 lines or columns to do the prediction of the block. And then in this case, we have a more precise prediction, but also you have much more complexity involved in the process. Well, we have also the matrix-based interprediction, which is the first learning-based solution in a video coding format. Basically, is a matrix multiplication, and the coefficients of this matrix are defined offline, naturally, using neural networks. Okay, but the standard have the predefined values trained by neural networks. Oops, sorry. We also have wide-angle interprediction. It's a novelty. Since now we have rectangular blocks, then we have some specialized tool to work with this type of blocks inside the that 65 angles that I tell you before. We also have inter-subpartitions, and we can have one block divided in 4 horizontal or vertical blocks, and then we can we do the prediction of one block here, and the samples of this block, this first block, will be used as reference for the second block. Then we have a data dependence here. These blocks only, this last block here only will be enabled to be encoded after all the other blocks are encoded. But using this solution, we have more coding efficiency and more complexity also. We also have a cross-component linear model prediction, where we are using the information for luminance and inferring the prediction from chrominance using the information from luminance. Then we can't repeat the process again. The position-dependent prediction combination can do a combination of predictions also to using some weights to define which is the best prediction. Then we have a lot of possibilities now inside the interprediction to define which prediction will be used. And then we must test out these solutions, and this is important. We need to evaluate all these opportunities to encode to define which is the best one. Okay, considering the interprediction, we have also sizes from the biggest CTU, 128 by 128 to 4x4, which using block sizes higher than the ones allowed by the HVC, and we have now 28 seal size, more seal size, and basically motion estimation and motion compensations are the same. But we have novelties. For example, you have the geometric partitioning mode. In this case, you can have a second partition after this seal definition, and then we have an angle and an offset of this angle, and we can define a better prediction using this type of tool. Then in this case, we are using, for example, here, a lot of small blocks to have this type of partition. And using the GPM, you can use bigger blocks and reach a better prediction, because now, for example, in this region, you have only green to be predicted, and then it's easy to get the best results. Okay, but again, we have more complexity with this tool. Another very important tool is the affine motion compensation. In this case, we use some additional complexity to focusing on other object movements than the translation, which is typically from the motion estimation until the HVC, the previous standard. Now we can have also scaling, rotation, shape change, and sharing. And in this case, we need more motion vectors. For translations, we need only one motion vector. But now, for example, in this case where we have scaling and rotation, from one frame to another, we have to have two motion vectors. And in this case, where we have also sharing, then we have to have three motion vectors to represent. Then we have more lateral information, but in some cases, this is advantageous, and we can have more coding efficiency at the cost of more complexity. Other important thing here is related to the standard merge prediction. In this case, the idea is to reuse the information of all this lateral information from one block to a group of blocks. Then we can reduce the lateral information. In this case, you can, I don't know if you can see now because it's very small, but you can, the original partition. And then here we have the lateral information grouping for this partition. Then we can have much less lateral information, but to do that, we have a lot of complex tools that allow us to reuse the first motion vector, and then we can get the history of other motion vectors. You can have the difference between motion vectors, and so on. There's a lot of tools here. And we have a lot of other tools inside the internet predictions that I don't have time to discuss with you, but the prediction with sea level weights, adaptive motion vector resolution, the coder side motion vector refinement, bidirectional optical flow, prediction refinement with optical flow, and so on. Well, we also have a possibility to combine inter and interprediction. There is one mode which is not inter, but a combination of both modes. It's a novelty. Then we can have a weighted combination of these predictions to get a new prediction which will be used. Well, considering the transforms and quantization, now the VVC allows bigger transforms than the HVC, but also allow transform over rectangular seals. HVC allowed only squared transforms. Now can have also rectangular transforms. And then we can have much more possibilities of transforms to evaluate. We also have the transform skip mode. As in HVC, the transform skip mode is only a mode to, in some cases, is interesting to not use a transform. That's a very specific case. And now we have three transforms that can be used. HVC used only the DCT2, but now you can use here the DCT8 and the DST7. Then now we have three transforms to be evaluated, and you can use different transforms in horizontal or vertical directions. This means that we have a lot of combinations of transforms to be evaluated, and this increased a lot the complexity of this model. We have also a fourth transforms, but it's a secondary transforms applied over the previous transforms, only for interprediction, which is low frequency, no separable transforms. Okay, it's also a novelty here. In terms of quantizations, we increase a little bit the number of the values allowed for the quantization parameter to 63, and also allowed the use of two scalar quantizers to define which is the best one. Finally, the entropy coding basically is the same used inside the HVC, the previous standard, with some improvements, okay? But they are using the same tool, which is called context-based adaptive binary arithmetic coding, CABAC. Considering the loop filters, we have inside the VVC the blocking filter and the sample adaptive offset, two filters present also in HVC, and we have two new filters, three at least, two adaptive loop filtering, one with cross component to increase even more the quality of the signal. And we also have a Luma mapping with chroma scaling. In this case, the idea is this filter is used only to increase the coding efficiency, okay, increase the compression rate. The idea is to modify the dynamic range of the input to better use this dynamic range and then increasing the coding efficiency. Well, the VVC when compared to HVC is 4 to 30 times more complex and have compression rates from 18 to 84% higher than the HVC. Then you can have much more compression at a cost of much more complexity also. Well, some trends, I'm sorry, I have a lot of time here, but I will try to finish. I like a lot of this graph from Zhang. Here he is showing the tendencies for the future, considering 5 axes in relation to visual signals. Quality, spectrum, view and angles and depth, time effects, and spatial resolution. And this yellow, this first yellow here is now more or less where we are today, and near future is the second yellow here. We are almost in this middle of these two yellows. But you can see here that, for example, in terms of quality, we start from low quality of videos, then we are increasing. Now we have videos with medium quality and almost high quality, ultra high, and the idea is that in the future is to have really realistic videos. Okay, for example, how many bits we are using for sample? 8 bits, as the example I said to you in the beginning. Nowadays we have a lot of applications 10 bits, and the idea is to increase the number of bits to 12, 16, 24 to 100 bits per pixel per sample. Considering the view angles and depth, the immersive experience, now typically we have the 2D videos, we have also stereo videos, some 3D videos, but in the near future, point clouds, I will talk a little bit about this in the next slides, and the multi-view and virtual reality with 306 will be very common. The idea is to increase a lot the immersion. And then in the future, the use of light fusion and volumetric solutions also are idea. Considering the time and frequency, nowadays typically you have 30 frames per second, but many videos also are using 60 frames per second. The idea is to have till 1K frames per second. And in terms of resolution, the spatial resolution, nowadays we have a lot of applications in Full HD, but now ultra high definition is also common for 4K, 8K, for example, and then the tendency is that we can have billions of pixels in the future. Well, here you have an example. It's not easy to see, I believe, but if you consider the videos, the resolution, the frame rates, the bit depth, the quality, and the view angles are increasing in all the scenarios, in all the axes in the previous picture, but also you can consider the popularization of different types of visual content. For example, 3D videos is common nowadays, 360 videos also, you know. Virtual reality, augmented reality, and mixed reality also is increasing in relevance. We have a lot of applications nowadays using this type of visual systems. Also have new types of visual contents like point clouds is the first example here at the center, where you can model objects or scenes using a 3D model with literally with points. It's a cloud of points, and then we can navigate around the scene or this object with total freedom. We also have light fields, like in this example here. Light fields is an example of image where you can, for example, refocus the images after we get and have a lot of other interesting information and another way to represent the information. Okay. Also, holograms is also have a lot of work with holograms, but from these three technologies, the holograms is the one that is not expected for the near future. Okay. Well, consequence of this the scenario is that you have expressive increase in the amount of data required to represent visual information in now access. Then we need more powerful code engines to support this type of complexity and this amount of data. Naturally, we have an expressive increase in the required computational effort, and this means that we have a lot of problems related to power, energy, and so on. And we need algorithmic optimizations, a lot of algorithmic optimizations, and hardware designs to allow the spread of this new technology, okay, these new ways of visual content. Then all the solutions must be built together. And in terms of opportunities, we can explore the high correlation between all these axes, spatial, temporal, view angle, texture, depth data, and so on. There is a lot of redundancies that we can explore. The use of machine learning and deep learning is very attractive nowadays. We have very good results using this type of tools. My group is working with solutions also, and we have very interesting results. We can explore massive parallelism, which are very typical from this type of data. Video allows the explore of parallelism. It's easy to explore. There is a little level of data dependence, and this is very good to be explored. And also explore heterogeneous systems. Then we can have a mixture of systems like that example I showed at the beginning with a GPU, where you have a dedicated hardware together to encode and decode together with the GPU cores. Okay, conclusions. Well, visual signal coding is still a hot topic. Video, 2D, 3D, and 306 point clouds, light fields, and so on, holography, and so on, are here. There are several challenges to realize visual signal coding, as I told you, and these challenges will only grow as time goes, because naturally the quality, we are interested in more quality, resolution, frame rate, viewpoints, and so on. Immersion is also a tendency. We want to have more immersive solutions. And have also new types of visual signals that requires much more data and much more complexity to be processed, like point clouds, light fields, and holography, and so on. Then the complexity of coding algorithms will increase a lot to handle this scenario. From the algorithm's perspective, ultra-low complex solution with high compression efficiency are essential to enable real-time visual coding systems. Then it's not easy to build this type of system, but we need to try. And learning-based solutions have shown important potential. And from the hardware perspective, dedicated hardware solutions provide high throughput and low energy consumption, and application knowledge-based solutions maximize the results. Understanding the algorithms is very important to implement dedicated hardware from these algorithms, not only generic solutions. Algorithms running on general purpose processor are not a solution interesting for many of this visual content that I showed to you. Well, I'm sorry for the problems. Many thanks. I'm available for questions. I don't know if you have time, but this is my contact. Please feel free if you have some doubts or so on.
Yeah, thank you very much, sir, for your valuable talk. So if you have any questions, anyone having any questions, you can ask. You can unmute yourself and ask. Anyone having any questions, you can go ahead with the question. I have make you to unmute yourself. If anyone having any questions, you can go ahead.
Hello, Professor. I have one question. Can I ask?
Yeah, yes, sir. I'll go.
Yeah. Sir, can you go back to slide 27 or 28? I don't remember exactly.
I'm sorry. I cannot understand.
Slide number 27 or 28?
27. I try. Where are you? Here.
Yeah, 27. Yeah. So I just wanted to ask, like, since the quantization operation is a lossy operation, like, how are you determining this quantization inverse process?
Okay. It's not easy to define. Let's try to answer to you. We can externally define the operation point of our system. For example, if you want requires a certain level of quality, you can define the quantization parameter as a fixed value. Okay, but we can also define the size of the file that we want to have. Then the compression rate. If you want to define the compression rate, then the KP value will change during the encoding process to guarantee that you have that size you define it. Then if you have, for example, more complex regions in a scene, then in this case, you required to increase the encoder we define to increase the quantization parameter exactly to allow the reduction in the number of bits. Then in this case, we lost some quality, but you guarantee that you have a fixed bit width at the output. Okay, then the encoders typically have this buff configurations, quality constant or bit width constant. And the quantization works considering these two options. Okay, but we can, for example, it's very common if you are using real-time applications. The encoders, if you have problems with the internet band, for example, with stable internet, then typically the encoders will increase the quantization parameters to allow a smaller block size, even with a lot of losses in quality, but with a smaller file size. Then in this case, you can still see something till the internet recovers. To increase the quality. Then this is also there is a lot of systems that do this type of operations. You can typically you can experience can see some applications like that when you have videos with low quality and high quality inside the same connection. Okay, I don't know if I answered your question.
Yes, sir. Thank you.
Thank you very much.
So any other questions, or we'll stop here because we already crossed the 10 o'clock because our next speaker is also ready. So if you know questions, if you have any question also, you can mail to sir. He can answer your question. So thank you very much, sir, for accepting our invitation and delivering a valuable talk. So on behalf of whole organizing team, I am very thankful to you. Thank you again. So
thank you, Professor Depak. It's very nice to be here with you.
Get back to you, sir. Okay, thank you.
Okay. Bye-bye. Bye-bye.
Bye-bye, sir. So we will go to our next speaker. So Dr. Professor Milan Biswal, sir, can you able to hear us?
Hi.
Hello, sir. So Can you able to share your screen, sir?
Sure.
Yeah.
Hello, everyone. Yeah. Hello, everyone. Yeah, I think I can share my screen. Yeah.
Yeah. Okay. So, so this is our keynote speech number 6, and today's number 2. So, on behalf of whole organizing team, I welcome Dr. Milan Biswal for accepting our invitation and delivering a keynote speak on this. His keynote speak topic is data analytics for smart grid opportunity and challenge. A short bio on Dr. Milan Biswal. Dr. Milan Biswal is working in the assistant professor of research in the computer science department in New Mexico State University, USA since May 2019. After completing his PhD in 2014, he worked as a postdoctoral researcher in Kilp School of Electrical and Computer Engineering from 2016 to 19. He was associated with Children's Auditory Research Lab, NMSU, as a research scientist. He has worked on several research projects sponsored by the US National Science Foundation, Sandia National Laboratory, US Department of Energy, US Department of Defense, National Instrument of Health. His research broadly focuses on signal processing, machine learning, and computational modeling solutions for challenge in the smart grid of auditory bioengineering. So on behalf of all the students and organizing committee, I once again welcome you, sir. Over to you, sir.
Thank you so much for your kind introduction, and thank you so much for the opportunity to, speak something here. And thank you everyone for your very valuable time. So the title of my talk today is going to be Data Analytics in the Smart Grid: Opportunities and Challenges. So here, typically I intend to share some of the broader viewpoint about the data analytics applications, particularly the data science applications that exist in the smart grid arena. So instead of being very specific onto the point, I would first go ahead and give a broader overview of data science applications in the smart grid. What are all the typical opportunities and challenges there? And then I would cover some of the specifics as well in the latter part. So, okay, the smart grid. So typically, I think everyone is aware about what the smart grid is all about. So before a few years, the electricity grid used to be entirely dominated by the power systems engineers, and it was a core electrical thing. But now, like as the time passed by, and particularly in since last 10 years, there has been a lot of attempt to modernize the electricity grid and bring forward a lot of like automation onto the grid. Similar to the revolution that happened in the digital technology arena, like internet, if we could add certain high-level automated controls onto the electricity grid, and that's how the smart grid basically started with. And right now, we have a plethora of opportunities in the smart grid. Typically, if we take the US electricity grid, it was first built in 1890s, and right now we have around 9,200 generating units, and we have a total generation of greater than 1 million megawatts, and we have 300,000 miles of greater than 300,000 miles of transmission lines. So it's huge. So it's super huge. So when you have a system of this degree, and when you try to modernize it and include new features, it basically brings up huge amount of efforts, as well as huge amount of opportunities to look into. So typically, when we are talking about the data-driven solutions right now, so smart grid is going to, the smart grid automation would be to a large extent depending on a lot of this data-driven solutions. So typically, if we look at the three pillars that basically bring the smartness onto the grid, would be first is a advanced communication infrastructure that goes in sync with the physical power grid. So we have a coexistence of the communication infrastructure laid onto the physical power grid. Then we have all the automation happening through the information technology, and we have automated controls happening uh, mm, in sync uh, with the controls. Okay, so going back to the data, so my focus today is going to be entirely on the type of data that exists and how do we propose different types of data driven solutions. So when we talk about the data, first the sensors. So in the smart grid, you'll find, or in the electricity grid, in a classical terminology, you will be finding something like intelligent electronic devices, which are associated with SCADA. So these devices, typically you have protective relaying devices, or the relays that basically are responsible for detecting faults in the system. Then you have tap changer controllers that basically decides about the transformer tap changes. Then you have circuit breaker controllers, capacitor bank switches, recloser controllers, voltage regulators, digital fault recorders. And so these are the classic devices that, or the legacy devices that used to exist in the power system. And these devices more or less operated independently and didn't require, most of them didn't require communications to be integrated along with them. But some of these IEDs, which are basically connected with the SCADA networks, they had communication, of course, but these communications were not real time typically. But then as the smart grid concept came forward. I'm sorry. Okay. As the smart grid concept came forward, we had new sensors, like we had phasor measurement units. Earlier also, we used to have phasor measurement units since 1960s or so. But those phasor measurement units were very sparse. There were only a few of them, and most of this data were not being used. But in the last few years, like last 5 or 10 years, we have a large number of phasor measurement units on the transmission systems, as well as we have in the distribution systems, smaller version of phasor measurement units. We call them as micro PMUs, or micro phasor measurement units. So PMUs are typically of two sorts. One is protection grade PMU, and another is measurement class PMUs. So these are typically, the signal processing algorithm that works in both these cases are a little bit different. And these mostly differ by the accuracy and as well as the frame rate sometimes. So we are going to talk more about that later. So typically the PMUs measure some, voltage phases, current phases, frequency, and rate of change of frequency. So I'll just go by the voltage and current phases, which are typically, if you have a current transformer or a voltage transformer picked up and it picks up the magnitude as well as phase, and then you sync it with the GPS, and these are and then also either from the voltage or the current waveforms you extract the frequency, and these all values are tagged together onto one frame, and they are typically, a PMU measures that as a single piece of measurement. And then we have sensors such as smart meters. Earlier, smart meters were not prevalent, but right now almost every household has smart meters. So what it does is it typically measures uh, the power consumption, but unlike a traditional meter that basically locally measures it and stores it, a smart meter typically, every 15 minutes or every 30 minutes, the total power consumption basically, transmits it to a central repository. We're going to talk about the smart meter architecture in a while. So when we have this kind of, typically the PMUs or smart meters, they generate a huge volume of data, and that basically gives rise to a lot of applications that can make the grid smarter. So we are going to talk about, I'm going to talk about few of these applications. So before that, what are the typical types of data that exists in the smart grid? Like any cyber physical systems, So we have operational data that are typically control, protection, and scheduling data. We have data for planning. So by data for planning, what I mean is like the data that can help us decide what kind of resources that needs to be added. uh, for example, if we want to harden a particular line to improve the resiliency, or if we want to add some redundant infrastructure to increase reliability of operations and things like that. So then we have data for archival, so which is typically like the data that are these are typically monitoring data that are stored for future use. So future use in the sense like in the event of some sort of blackout or something, and if you want to know about what possibly caused this kind of things, so which you call as event root cause analysis. So that's basically the data for archival basically determines most of this post-mortem or event root cause analysis. Then we have data for energy markets. So these are typically related to demand response. Demand response. So I think as the name implies, it's more related to the energy market. So it basically so in the smart grid, the typical flow of like in the traditional grid, we used to have only flow of energy from the producers to the consumer side. But with the advent of the smart grid, we have bi-level, like we have both way flow of power. So that means that energy is not just transferred from the producer to the consumer, also the consumer, if they have a solar or some sort of like distributed generation associated with like distributed generation, or some sort of maybe a battery storage or something, they can also pump in power onto the grid or energy into onto the grid, and it becomes a two-way flow, and it basically introduces something called as a transactive energy system, whereby the cost of electricity. So you just don't buy electricity, you just don't buy electricity from the grid, but also you sell it to the grid, and the pricing, the dynamics of pricing entirely differs. So these are the typically all the data that are there in the smart grid. You can more or less put them into these four categories. So now, how does this data map onto the big data arena? So right now, big data, since last few years is again another big thing. So it's basically an enormous amount of data that comes up. So looking onto the big data, if you look at, there are four pillars of big data. The first thing is volume. So it basically requires that you should have huge amount of data. And so a typical PMU produces per day more than a GB of data. In fact, it also depends on the frame rates and all. It could be a lot more. Then even if you have a micro PMU, so these micro PMUs are smaller version of PMUs that are on the distribution system. Typically, there are a lot of them, and they are also being aggressively being deployed. So these micro PMUs also have similar kind of data volume. Then we have data from the advanced metering infrastructure, which are essentially the smart meter data. We have SCADA data as well. So this data, so the data volume is used to put them onto the big data framework. Then the second thing is veracity, which talks about the trustworthiness of the data. So most of these data that are generated, they are typically maintained by a typical utility. So these sensors that are deployed on the power system are maintained by a particular utility, and the consumers, they basically subscribe to the utility programs, or the utility maintains most of these sensors. So we have authenticity and origin about the data, availability about the data, and we have accountability of the data. And we also have uncertainty, certain types of uncertainty associated with the data due to the communication failure or something, some other kind of adversarial events or something. So then let's talk about variety. So we have a lot of different types of data in the smart grid. It's not just certain voltage or current sensors or the frequency data. We have power consumptions, and we have lot more other type of data. And moreover, we can also use for example satellite imagery sometimes to to know a particular, adversarial, adversarial event, for example, a natural disaster, and then take like those imagery analysis to integrate them with the with the data available from the grid states or grid controls, and take some sort of actions based on them. So we have a variety of data. Then the velocity, so frequency of the incoming data. We have real-time data, like so PMUs are not really, they are mostly near real-time data. On the smart grid, we typically don't have real-time data as such. I mean to say, like, but so with certain, although it might not be that in real time, it's not like other domains, but we could call them as most of these data to be near real time or streaming data. So then, so when we combine all these four, then we typically encompass value. So these are typically the terms that are associated with the big data and how they map onto the smart grid. The typical field of the smart grid. Now coming to the data analytics on the smart grid. So whenever we start with data analytics or data science, there are two terms that, there are two types of analytics that comes into picture. One is prescriptive analysis and analytics. So by prescriptive analysis, you prescribe something. So it's like a decision support system. You have certain data, you extract some sort of information out of it, and that information sometimes helps you take some sort of action, or some sort of, be it a control action, be it something. So prescriptive analysis typically takes care of that. Then we have predictive analytics. In the predictive analytics, it's more about modeling the system and making some future predictions. So so in this talk, we are going to talk about like a few examples of the decision support system and one example of the energy management system. So typically in prescriptive analytics, we can also talk about, like, there are several other applications, such as, you can the data that gets generated from the systems monitoring, you could basically use it for the cyber physical system security, to detect different kind of cyber attacks, as well as mal operations in the system and things like that. And you can also use the data to have something called as a resiliency oriented design and operation. So by resiliency oriented operation, what it means is, whenever there is let's suppose there is a natural disaster or some sort of a cyber attack or something, some adversarial event happens, how does the grid basically manage the resources that are there within itself to minimize the damage, or to mitigate the particular adversary that gets generated. So now, if we want to classify all these, data analytic applications based on certain, data analytics serves based on applications, we'll see that, events and disturbance monitoring is one. So then state and situational awareness. So state estimation means that, you have certain measurements available and you want to have a information regarding this, the state of the physical system. So you have state estimation for the, particularly for the, for the transmission system, state estimation is not a big problem. But if you want to estimate the state of the distribution system, it's increasingly challenging, because you have the states changing quite dynamically. And then you have customers and prosumers related data. So this prosumer term is like producer and consumer together becomes prosumers. So in the smart grid, instead of calling the consumers as just consumers, you mostly call them as prosumers if they have their some generation of their own. So then there are applications such as something called as a customer baseline load. CBL or customer baseline load is typically used for energy markets. So particularly in the transactive energy systems, then you have customer behaviors, like, you can use those data to categorize different types of customer behavior and so forth and so on. And then you have operation and control related data, where these are basically operational data that can be used for energy management systems, protection, stability monitoring. We're going to talk. Okay, now an example of the prescriptive analytics and some of the work that we have done in this area. So first, I would talk about PMU data analytics. So by that, what we mean is if we have monitoring data available from different PMUs that are placed on different geographical locations, at different geographical locations, and all these PMUs are connected typically onto one repository called as a Fraser data concentrator. And the Fraser data concentrator, so there are several in smaller regions, there will be, for each region, there will be a PDC or a Fraser data concentrator, and several Fraser data concentrators together report to something called as a super PDC. And all these data are kind of, you can call them as near real time. And they have communication infrastructure supported by either optical fibers, or so mostly optical fibers. And so PMUs typically measure these operational data and send them on to the PDC, and the PDC to the PDCs to the super PDC. And then, okay. So what can, in PMU data analytics, what are the possible applications that that exist? One would be supervisory protection. This is one area where I think we did some early works on this particular area. Then stability monitoring, then state estimation, postmortem analysis, event root cause analysis, and so forth. And when you have PMU data available in the distribution systems, there are typical applications where you can use them. For example, microgrid protection tasks, you could use them. Maybe one of the most important applications would be topology identification, sometimes for power quality monitoring as well. So when we started working on this back in 2014 around, so the first thing is to, when you want to, so we wanted to design a supervisory protection system, and we needed to generate a lot of simulated data, because we can't get that much real data from the utilities. And of course, the utilities would be quite conservative about sharing a lot of their they typically, most of this data would also be unlabeled. So when we were talking about generating data to create a data-driven solution, so now the data has to very well correspond to the kind of data that exists in the in the typical cyber physical system, or on the physical system. So for that reason, we started with so we didn't have any literature that basically suggested how the PMU data, like what sort of what would be the noise distribution of the PMU data, or what are the uncertainties typically associated with the PMU data. So we have power system simulators that basically and then we can generate simulated data, but those data might not, and in most cases they do not correspond to the data that we see in the field. So there we started doing some work, and then there are two sources of uncertainty in the PMU data broadly. First is due to the variation of the load, and the second thing would be measurement noise. So and one challenge associated with estimating how much noise would be there or how much uncertainty would be there is the sampling rate of the PMU data is pretty low. It would be either 30 samples per second, 60 samples per second, or 120 samples per second. Typically, if we have a speech or some sort of that kind of signal, we'll have 44,100 samples per second. So compared to that, it's a very low sampled kind of sparsely sampled data. And then we had to estimate the noise associated with it, or the uncertainty associated with that. So so in the early stage, we used a very simple method we did a simple median filtering to extract the uncertainty that were associated with the data. And I won't go to the details of it, but there could be more sophisticated methods where you could be basically use the instruments and particularly the PMUs on the lab and find out what would be the exact distribution. But when we first studied it, we did it more like we did all these experiments on the real PMU data or the field PMU data, and we had three different sources of PMU data at different voltage levels. One data was at distribution system level at 120 volts on the, typically the household supply level. Then we had at 20 kilovolt level and 340 kilovolt level on the transmission side. So, and then our results indicated that we found that a typical Gaussian distribution, that's something which is pretty much expected, but our key contribution was like we verified that the uncertainty distribution or the noise distribution was Gaussian, and if you use a typical power of 45 dB, that typically talks about that typically describes the amount of uncertainty that were associated with the PMU data. This is a work that we did somewhere around 2016, and a lot of new literatures are available, but it's still like when you generate this simulated PMU data is most of like this is one of the early literatures that basically talked about the noise distribution. So now, what are the challenges that still exist? So the first thing is that how do you filter out this noise? Looks very simple. You could simply put you could say that, okay, we could generate a simple low pass filter that would basically filter out the high frequency noise, but that's not the reality because the PMU sampling rates are pretty low, and uh, simple low pass filtering might not be a pretty good solution. Then the second thing is that so in such scenarios, how do you filter out noise alone? You don't need to filter out the typical. So sometimes what happens that whenever you have a particular disturbance, so these PMUs respond to them like the voltage and current waveforms that basically gets altered because of that. The phase also, of course, gets altered, and those signatures you don't want to lose. So you want to filter out noise alone and preserve the signatures. That's one challenge. Then the other thing would be like, how do you detect bad data whenever, like, if you have NANs in the data, or like NANs exist when you either the PDC, when it receives the PMU data, certain data when gets corrupted in the communication channel for some reason, or maybe due to the measurement errors, or things like that. So we have a lot of that kind of bad data or missing data on the PMU. So one of the typical research direction would be like, how do you basically substitute for that? Looks pretty simple, but it's sometimes very much challenging, typically because of the low sampling rate that is associated with it. So one of the ways to deal with that is you look at the entire system level. So you have multidimensional sensors in a way. So you don't have one PMU, you don't look at one PMU, but you look at PMUs over an entire geographical region, and you basically integrate the system state or the power system, like the physics of the system, and then all this sensor data to fill out the missing data that to estimate what would be the bad data or the missing data. So now the other challenges would be like if there would be some sort of false data injection attacks or some sort of data manipulation attacks. So whereby a typical PMU knowingly does some sort of let's suppose a PMU is compromised and has been sending some sort of erroneous data, then how do you detect them? So there, what you could do is you could have data from other sources like SCADA or something, and then map them onto the PMU data, or how that's another research direction that can be taken forward. And then, of course, you can use PMUs for state estimation. So these are certain challenges that still can be addressed. Now, looking onto the second thing. So the second thing that we looked on to was how do you like are there any challenges associated with the archival of the PMU data? That's also, again, the problem looks pretty simple. You will basically collect them and dump them onto the storage. But the typical problem is this data volume is pretty high. Although the sampling rate is low, but the data is continuously collected, and all these PMUs basically report to the PDC. Then the PDC has to send it to Super PDC. So the data storage and transmission is definitely a challenge all the time. And we saw that not much literature had focused on typically archiving the PMU data. So we did. And can we use standard compression approaches to compress them? Yes, of course we can do. So, but if we use lossless ones, well, that's fine. But if we can there be a better way? Because the data that exists in case of PMUs, most of these data are correlated, because they although these PMUs are placed on a geographical locations, they would have certain degree of correlations, because they do not differ by differ. There would still be a lot of correlation among the PMUs in a particular region. So in order to do that, what we did was, can we have a lower dimensional mapping? So like a principal component analysis or a eigenvector mapping. So where we could basically transform all this data to a low dimensional space, which will have the compressed representation. So we thought about that and did some work on that. But there was another problem. So that would be a lossy approach, of course. So when we do a lossy approach, it might happen so that we might still lose some critical information. So now we are removing some redundancy, and we are having a compressed representation, but there could be some loss of information, and that's something which is shown here in this particular figure. If you look at the the original data and the reconstructed data, so we see that this is a typical fault, and you see that the magnitude has been clicked off. So what we did was, we employed a statistical change detection method, and what we did was, like whenever you have steady state and you don't have any disturbance or you don't have any event, compress it in certain lossy way, and whenever you have a change there, then you can go for a more faithful compression. So typically we did another approach as well. So what we did was, the spatial redundancy or the correlations that were existing because of the geographical region, we basically dealt with them with PCA, and the temporal redundancies that existed, we used simple concepts like DWT and discrete cosine transform, which are basically used in JPEG. So to compress the data, and we got really pretty good compression accuracy. So it's basically it's also one of the early phases of work on PME data compression. We got a overall compression ratio of around 31.39. So what next? What are the opportunities lying here? So
наш украинский этот самый, который ехал на санках,
so sorry. So one of the typical thing would be, like when you have cloud storage, and when you, typically the application domain is changing in a bigger way. So this PMU data, particularly the micro PMUs, and also how do you build a cloud infrastructure, or how do you manage those storage as well as management of those micro PMUs data. That could still be. So what I'm talking here is more from the perspective of computer science and related applications. So now the third one would be monitoring. So it's basically, again, this is a typical application of the prescriptive data analytics. So one of the typical application would be decision support system. So making a decision support system that could add something called a wide area monitoring, protection, and control system. So what it means is, the situational awareness data, or the situational data that is collected from the PMUs, we basically develop a decision support system that basically takes different action. So okay, so I'll go quickly through it. So typically the idea is that, we get data from multiple PMUs, and then we detect different kind of disturbances that could be possibly be existing. So we'll be detecting them, and then and all this PMU data, we can use them for stability analysis. Then we have a disturbance detection and identification system. There we could use machine learning or signal processing based methods to classify different kind of disturbances, such as a load switching or a capacitive switching or a generation loss or a or any other typical, like faults are typically the ones, different types of faults are what we are looking at. And this basically provides, so to protect the grid, we already have the protection infrastructure in place. So relays always already are doing the local relays that are deployed in the power system does the job. But our job here, based on the PMU data, was that, so we provided a supervisory layer to it. So basically, any fault that gets past the, let's suppose, the local relays, if the local relays fail to detect them, maybe the primary and the secondary protection fails. So even the joint protection fails. So if then in that case, what we could do is we can use this supervisory protection to validate the flags issued by the local protective relays, and we could add additional level of protection onto the grid. So that can basically protect the grid from 2003 kind of blackout that happened, or in the US, or type of, the event, the blackouts that happened because of the relay misoperations. So now going on to the other page. So here, so we can use, so in the disturbance detection and identification ways, we could use machine learning based techniques. So typically when we have, let's suppose if we use machine learning based decision support systems, which are typically, the case here. So we did a simple, we proposed a simple convolutional neural network based event detection scheme or event classification. Excuse me. So, okay. So sorry about that. So where what we did was the voltage and frequency data that were collected by the PMUs, we basically created a pseudo image out of it, and we kept this pseudo image as a input to the convolutional neural network to classify or to identify the events. Now, the interesting thing is there has been a lot of work on this particular. You'll find a lot of literature using convolutional neural networks, and so typically the deep learning techniques to add on to perform prescriptive analytics or do classification and tasks like this. But one thing that we wanted to look onto is, can we launch an attack on this particular system? So we don't have to really get into the machine learning system, but can we have a black box attack? So can we manipulate the PMU's data in certain locations in certain way, so that we could fool this decision support system? And that was motivated by typical the black box attacks, where you see that there is a panda there, and if you add a small amount of random noise, so it still looks like a panda, but it's perceived like a gibbon. So motivated by this this approach, so what we started doing is, what we did was, we added small amount of noise onto the pseudo image that we generated to change the class level from the true class level to a different class level. And to our surprise, we found that around it was around 10% decrease in classification accuracies. So what we could do is we could still orchestrate a huge number of attacks. So here it needs to be noted that if you can make one such attack to fool the decision support system, and if you do certain local certain locally coordinated attacks, then you could probably bring down the system. So And how do you basically know that, we have this data as a pseudo image? So what we did, the manipulated pseudo image, we converted back onto the PMU mapping, and then identified what are the typical PMUs that we need to modify by certain amount so that these attacks can be orchestrated. And we were pretty much successful in that. So one of the ways to prevent this kind of black box attacks is that you basically make your machine learning models pretty much robust, and make them well well generalized, or you have to regularize the ML model in certain way that there are very little scope for the black box attacks. So that is somewhere there is a lot of scope for further work. So this is something which we did recently. Then going to the predictive analytics part. In the predictive analytics part, so what we did was so here we used the advanced metering infrastructure data, so or the smart meter data. So here the smart meters are typically placed on the household, and they measure these energy consumptions. So when you have measure these energy consumptions, you could have the EMS application associated with it, like a Google Nest kind of a device that can basically control certain appliances in the home. So there will be a home energy management system. And so typically one of the so in the AMI and home energy management systems, so we took a typical application. I'll go directly onto the application, and I'll talk about the predictive analytics that we did with it. So okay, so okay, so one application that we looked onto was forecast energy consumption of every household. So if we know the future energy consumptions, then we could know about the possible adjustments, or the load management that, or the home energy management system, how to manage the home energy management system. That's one. The other thing is that all this smart meter data, the smart meters that basically collect data from each of these households, they need to send all this data to the utility, so that the utility could possibly use them for knowing the aggregated load forecasts and managing their resources, and to fix prices and things like that. Now here arises a big issue. That issue would be data privacy. So the users will not be willing to directly send their smart meter data, because those data could reveal certain really sensitive information, such as their availability at home, or what kind of appliances they are using, when are they using, and things like that. So data privacy is typically a major issue there. So what we did was we proposed a federated machine learning based infrastructure for that. So what we said, if you are using machine learning models to predictive machine learning model to do predictive modeling tasks, or to predict future energy consumption in the local smart meter levels. So what you could do is, instead of sending the raw data to the utility, what you could do is you could send the machine learning models parameter to the utility. So that way what would happen is, these model parameters are an encoded representation of the raw data that the smart meter senses. So that way, that basically, you are sending certain information that are required by the utility, but what you are essentially doing is you are preserving privacy of the individual. So that so a typical federated machine learning infrastructure looks like that. So typically it's the AMI infrastructure. Instead of sending the raw data, you send the model parameters to it. However, the federated machine learning has its own problems. One of the major problem is that so the federated machine learning is still vulnerable against inference attacks or poisoning attacks of the ML models. By poisoning attacks, what happens is that if certain smart meters are corrupted in certain ways. So what we could do is we could corrupt the machine learning model that basically is associated with the with the home energy management system. So, and then the other thing is that something called as unintentional memorization. So the machine learning models could memorize some of this raw data in the process of learning. So what we did in order to resolve that particular issue, we looked onto something called as a differential privacy. We're going to talk about that in a bit. I have 5 minutes there. So, okay. In federated machine learning, we use something called as secure aggregation. So the point is, like, if we want to avoid or if we want to get rid of this inferences, like inference attacks or typically poisoning attacks, we could use secure aggregation in federated machine learning and to avoid anomalous contributors. Now, in secure aggregation, what we do is typically one of the widely used approaches would be masking with one-time pads. So as you can see that, the users themselves have to exchange certain information among each one of them. So federated machine learning is a pretty established concepts for cell phones and other kind of data. So there, what you could do is you could still exchange this one-time pads or OTPs with each other. But would it be possible for the smart meter infrastructures? Possibly not. So for that reason, what we did was we said that, why not use differential privacy? So in differential privacy, what we do is the machine learning parameters, what we have. So we could add certain amount of calculated noise. So just to make it pretty simple, it would be a calculated noise in certain way that it basically preserves the data utility, but it it doesn't affect the utility much, but it adds certain amount of uncertainty to the data so that the privacy is preserved. So typically, I won't go in details onto that, but differential privacy is a like the whole idea is that you can see here that we have two terms, epsilon and delta. So where epsilon is a privacy loss parameter, or that's called as a privacy budget that controls the privacy and utility. So if the privacy is more, the utility could get compromised in the process, and vice versa. And delta parameters counts for a small probability, so with which it basically provides upper bound for the epsilon. So we used a local differential privacy here. That means that we embedded differential privacy at the smart meter level or the local machine learning model level, and then we used differentially private stochastic gradient descent. So typically, when the machine learning model was being trained, that's the time at which we basically introduce the differential privacy instead of training the model and getting those trained parameters out of it and then adding differential privacy onto it. We basically added embedded differential privacy along with that. And then we got some pretty interesting results. The first thing what we got is with federated machine learning, we found that the individual smart meters, their prediction accuracy increased. So here I forgot to mention one thing, that in the federated machine learning infrastructure that we proposed. So every 24 hours, the global model that we create, or we fuse all these local models that we take from the local smart meter, and we create a global model that is substituted onto all these local smart meters or the local home energy management systems associated with the smart meter. And then they keep doing their prediction again. And we found out that the mean absolute error as well as the normalized root mean square errors, they basically reduced significantly, as you can see here. So what we did was we did this experiment over a comprehensive set of smart meter data. We basically took around 500 smart meters, and we divided them into 10 clusters, with every cluster 50 smart meter. No, we had basically, I think, 100 smart meters each cluster, and then we had 10 clusters, so 1000 smart meters. And we found that for each of these clusters, the prediction accuracy or the forecasting accuracy improves, or the error decreased. And we found that these are all the privacy budget. With different privacy budget, you will find the NRMSE and MAE to be to be more as the epsilon value goes down. So we found that epsilon value of 8 would be a pretty good choice. So that will So it's a trade-off between the privacy as well as the utility. So utility would be inferred by the MAE and NRMSE associated with it. So epsilon is equal to 8 differential privacy with the delta value of 10 to the power minus 5. Happen to be pretty good. Okay, so I think I'm done with it. So there is a lot of other opportunities that and a lot of other applications that are there for descriptive as well as predictive analytics. So and then there like all these data driven solutions could be used for cyber physical security, for anomaly detection to detect different kind of attacks on the power system and so forth and so on. So one last note is I didn't talk about the physics based models. So I just talked about the data driven applications or the data driven solutions for different applications in the smart grid. So one thing that should always be integrated is the physics and the data driven approaches should go hand in hand, typically for CPS systems like smart grid, so that the data driven systems alone, I think should not be trusted in many scenarios, and you could have physical verification, and that could be the way forward to go. With that, thank you so much, and if you have any questions, I would be happy to answer. Thank you so much.
Yeah, thank you very much, sir, for your wonderful talk and valuable talk. So if you have any question, anyone having any questions, you can, 1 or 2 questions I can take. Anyone having any questions? I have unmuted. If you can, if you want to you can unmute yourself and ask question. I have make you to unmute yourself. Any question if you have? Anyone, if you want to ask any questions on data, machine learning or anything, you can ask. No? No questions, sir. We can stop here. Thank you. Thank you very
Thank
much.
You so much for the opportunity.
For accepting our invitation and delivering a wonderful talk. So on behalf of whole organizing committee, I again thank you very much. Thank you. So we will get back to you, sir. So thank you. Thank you.
Certainly. Thank you so much. Okay.
Yeah, Bapaditya sir.
Participant, please wait. We can start our next presentation, next workshop that on national instrument. I just call the Basant Kumar sir.
Hello, sir. Very good morning. Can you hear me?
Sir, I hear you.
Yes, sir. Yes, sir.
Okay, sir. So we can start now. So I welcome Basant Kumar for this session. Basant Kumar, I just introduced Mr. Basant Kumar. Basant Kumar graduated as a Electronics and Communication Engineering from Anna University, Chennai. He has a 8 years experience on National Instrument Technology. Also, he now associate with VI Solutions Bangalore as an assistant manager. Mr. Basant is handling major responsibilities of supporting various industries in implementing several turnkey systems and system integration projects using National Instrument Technology. Basant Kumar as the first and only certified professional instructor in National Instrument and CLD certified for the India, Russia, America, Africa country. He has delivered lectures more than 150 Indian engineering institute and industries. Also, he had conducted more number of hand-on training program to industrial experts of various domain on LabVIEW and basics and data acquisition. Now I welcome Mr. Basant Kumar in AISP 2022 forum, especially these workshop sessions, to deliver a talk with some National Instrument experiment tools. I over to you, sir.
Thank you. Thank you so much, sir. I'll quickly share my screen. Please just confirm me that whether you'll be able to, we are able to see it.
Okay, yes, sir.
So I've just minimized it. And I'm opening my PPT. So is my PPT visible to you, sir?
Yes, sir. Yes, sir.
Okay,
It
sir.
is perfectly right.
All right. Okay. First of all, I want to thank your management to giving me a great opportunity to be a part of this technical talk. I was going through the agenda, complete agenda. I was very impressed with the speakers and what are the topics they're covering. So I'm really obliged to be part of this because it's a great honor to be part of this kind of an activities. So thanks for the introduction also. And as sir was saying, Roy sir was saying, I'm a certified professional instructor from National Instrument, and I'm a part of VI Solutions also. And today's topic is going to be about AI in automation, because when I talk about National Instrument, NI technology, NI stands for National Instrument. Well, let me make it clear first of all, because the heading itself, the topic heading itself says what I'm going to talk about now, automation in NI technology. This basically NI means National Instrument technology. So National Instrument is one such company which are leading automation handling company. So most of the industries you will come across will be using NI technology in various parts, production or testing, or it can be various things. Okay, so they are part of it. And how we people in NI technology, we are using AI systems in automation. I want to tell you. For that, I'm going to quickly tell you how automation level, how things groomed slowly. Okay, so how things kept moving slowly, I'm going to tell you on that, right? I'm going to quickly tell you about what is the vision of this program. The vision of this program, first I want to talk to you all about Industrial Revolution 4.0. This is a very vital thing. I want to talk to you all about this. The reason is, this is where people will understand why artificial intelligence is basically needed when it comes to automation. All right, so what are the different progress over the past century, not even century, even beyond that, 200 years or 150 years of in the engineering revolution in industries, how it is happening. I want to just quickly talk to you all about that. The reason why I wanted to focus on this is because most of the people who are looking coming from college level, who do a lot of research work, students do projects, students do internships. I want you people to know what are the new technology, new scopes coming in, what are the new job opportunities coming. So when I talk about this, you'll be able to understand what are the things that are going on in this entire world in engineering automation level. So you people can also make yourself publish some papers, or do some research works, or do some R&Ds, or even your internship for your students. You can recommend your finalist project of your students, you can recommend on these things. So I want to tell you about now how the entire things are now moving. What is the future scope for industries? I'm going to talk to you all about that. Then I'm going to tell you about what is the role of artificial intelligence, especially machine learning and deep learning. Right? Why I'm more curious about machine learning and deep learning is there is also neural networks, and there is also no other subsets of AI. The very keen reason why I'm just more concentrating on MLT and deep learning is National Instrument provides huge support on machine learning and deep learning. Also, they support neural technology, neural networking. They support that. But machine learning and deep learning is the one thing. National Instrument have some toolkits, have some ready-made examples, have some proper guidance to start developing from the scratch. So I prefer talking much about machine learning and deep learning. But also I'm going to talk to you all about industrial IoT. The reason why I want to talk to you all about the industrial IoT is without communication, the artificial intelligence is incomplete. So when it comes to a complete automated system, when I come to a smart factories, where the entire system is automated, the entire production is automated, artificial intelligence is basically needed. It's barely needed. But without IoT, AI becomes incomplete. That is where I'm going to talk to you all about how the role of industrial IoT is part of this machine learning and deep learning. I'm also planning to show some demonstrations where I will try to develop some simple codes to you people, because it's a very short period of 2 hours to show you the entire process of from the scratch of training and developing, and even testing or comparison or classification, whatever you want to do. It's going to be a tedious task to do it within a 2 hours of period, and it might be not catchable for you people. So I'll make it a simplified version. I have a simplified version where I'll be trying to demonstrate that. And even for IoT, I'm planning last 15 minutes to 20 minutes for IoT, where I can just quickly show you, how I can just quickly design a cloud. I really wanted to show some, open source, so that, the students, the faculties for R&D works, they can, very freely use it, rather than, being a, because when it comes to IoT, it's a big business. Really, it is a very big business. In market, you will see, a lot of platforms which are like paid platforms are available, but there are also, unpaid platforms, which is highly sufficient for you people, for industrial, IoT, for research level, right? So because we are not more into an active clouds, or we are more into passive clouds, because we always want the data to be communicated. We are not more into do the computations in the cloud level. All right. So for you people, it will be sufficient if I can show you some open source IoT application platform. So the agenda of the program is going to be in 3 sections. Section number 1 is going to be, your industrial revolution in and outs. Section number 2 is going to be artificial intelligence, where I'll try to demonstrate some of the machine learning algorithm, and I have some, case study application videos also, which I'll be, trying to play you people and try to explain you people how it works. And it's going to be Internet of Things. Before going into section number 2, after completing section number 1, I'll show you a simple demonstration of the toolkit which I'm going to use. The platform which I'm going to use today is going to be your LabVIEW. LabVIEW is a National Instruments product. Okay, it's a toolkit where you can design all the engineering related application. It need not be specifically, it need not be engineering related to electronics, engineering related to communication, engineering related to civil department. It need not be so specific. This toolkit is designed in such a way complete solution of engineering can be derived from this toolkit. That is what this particular toolkit is being designed. So I'll be happy to show a very glimpse of how this can be started for the beginners level. And I hope there are some students also who will be beneficial out of this, who are watching here. And faculties, I don't know how many faculties are good in working on NI technology, because this is commonly used in industries. I'm not sure how well used in academies, but I'm pretty sure there are some institutions which are using this for research works. They're promoting for the students also to get some certifications. So I'm not sure whether you'll be knowing or not. So I'll be going with a very basic demonstration for a couple of minutes. Then moving into, I'll be jumping into how artificial intelligence and in IoT will be working. All right. So quickly jumping to section 1. Ultimately, when I talk about Industry Revolution 4.0, there is also something like Industry Revolution 1.0, 2.0, 3.0. Then comes 4.0, right? So what does 4.0 aim? What is the motive? What is the vision? Very simple. The vision of Industry Revolution 4.0 is to design smart factories. So ultimate goal is to design some smart factories. So when you talk about smart factories, there should be some criteria, because that's the reason I'm just put it into double quotation. Can you see that? So what should be a smart factory? What are the things should be included into a smart factory? What are the parameters? What are the criteria? What is the standard? Because every industry has their own standard when it comes to production. That's why every product comes with ISO or ISI certified product, right? So the standard has to be followed. So what is that standard? Whether Industrial Revolution 4.0 talks about the standard, I'm going to tell you all about that. All right. So when I first talk about Industrial Revolution 1.0, let me start from the beginning. That's the very first time where mechanical models were designed. When I talk about mechanical model, these mechanical models were powered by steam and heat. So water vapors or the burning coals, whatever maybe it is. Basically, they were powered using steam. Okay, this was marked at the end of 18th century, and it was the introduction to water and steam power mechanical models, right? So if you've seen olden movies, for example, I could give a very quick example of a Titanic movie where you can see at the ground level, at the bottom level, deck level, what happens is when they were running over there, you will be seeing that now people will be putting the coal, they'll burn the coal, only simply to burn it and get the steam power out of it. And the engine turbines will be moved using the steam power there, right? So that was the very first time, human beings started doing everything, using mechanical model. It was marked as I told you, it was marked at the end of 18th century, somewhere around 1780s. Okay. The highlight of Industrial Revolution 1.0 was, steam locomotives, steam engine locomotives. Now you have seen the steam engine, railways, that is the highlight. Then comes Industrial Revolution 2.0. Industrial Revolution 2.0 is actually an upgrade of 1.0. So where, excuse me, there were no, the same thing of mechanical models were being used, but one thing is that was used in a mass production. What I mean by mass production is you will have, huge factories where there will be, hundreds and hundreds of machines. There will be some operators who will be trying to control these machines, and these machines will take care of the product they are designing. They also have conveyor belts. Conveyor belt is nothing but that moves because there are a lot of machines there. So rather than moving them manually from one station to another, there are like stations. Whatever you see here is a different stations. Okay, so you can see throughout this building there is a lot of machines and stations there. So they use conveyor belts. So the conveyor belts were moving the products from one station to another, right? So this was marked at the 19th century, which means that around the 1850s, 1840s, and introduction to electricity, mass production, assembly lines, and mobility, along with telegram, was the highlight, right? And a gentleman named Henry Ford. No, Henry Ford is no one. No, he is the person who's the pioneer of the Ford company, automobile, whatever we see here, the Ford cars, whatever we come across. So he is the one who who was the pioneer of that. So he carried this process from food production sector, because this was first introduced to food production sector, where they were doing processing of food. Okay, food processing was happening. So from there they moved it into automobile. Okay, so the highlight of Industrial Revolution 2.0 is we are still using these kind of products like electric locomotive, the electric trains, whatever we see here, using the cables, it gets power. Over the top of the train, you'll see the cables. Even nowadays, you go to some metro cities in India or all over the country, all over the world, you'll be seeing, the trams. You'll be also seeing, the what I can say, metro rails. So these are like, electric powered automotive vehicles. Okay, so then comes Industrial Revolution 3.0. It is once again the upgrade of 2.0, where even now we have a mass production. Even now there are assembly lines. Even now there are like conveyor belts which moves the product from one station to another. But one difference is we replace the human beings who were operating these machines to robots. That was the first time we were trying to do it, and it was done by Henry Ford, as I told you. So now if you see like all the big shot companies like automotive companies, or you can see bus designing companies, space shuttle designing companies, you'll see that all these companies uses robots basically. What is the common robot they usually uses? A robot named KUKA, K-U-K-A. This is the robot people usually use in industry level. So even here you will be able to see that there are some n number of robotic arms, orange color items, whatever you see at the sides, they are the robotic arms. You can see that parallel arms are working on one particular car design. Okay, the welding, plating, painting, all these things happens through a robot. Testing also for a minor level will be happening through robots, and then comes the other levels of testing, safety test and other things will be tested using human assist, where human being will be monitoring. There will be some sensors included, there will be some dummy models included, and they'll be doing testing. But still there you will see that no human beings are involved. Human being involvement is there still. That's what I'm trying to say. So this was marked at the 70s of 20th century, which means that 1970s. So introduction to partial automation using memory, programmable controls, and computer. What it means is we were partially automating, which means that it's called a semi-automated. Industrial Revolution 3.0 gave you the products or the robots which are partially automated or semi-automated. What is semi-automated? It's very simple. Even in your homes, you'll see washing machines are semi-automated washing machine, fully automated washing machines, right? So what is a semi-automated washing machine is very simple, that it needs all the input from you, from a human being, who the user used to set all the data in there, and once he sets, it will be trying to do the particular task. For a washing machine, the task is to wash the cloth. All right. When it comes to other robots which does their own things, right? They have their own set of algorithms or set of program sequence which is running internally. Okay. So now we are spread in such a way that entire industry is having fully semi-automated application, which means that they are not fully automated. I'll tell you what is fully automated. Semi-automated is something like it always needs human beings input, and verification should be happening through human beings only. But the process of executing a task, for example, as I said, you go to ATM machine, it takes the input from you, but counting the how much rupees you are withdrawing, or counting what is the balance, checking how much inputs or how much transfer has happened in the recent time, because you go for the bank statement, right? All these tasks of maintaining these things will be still programmatically happening through robots. ATM machine is one type of robot. Okay, a machinery it's not doing a task is basically a robot. Okay, so washing machine is one such thing. Your AC is one such thing. Anywhere you go, there is a machine which is doing some tasks. It's basically a simple robot. Okay, so what is the highlight of Industrial Revolution 3.0 is robots that can perform program sequence without any human intervention, which means that once it starts, you're supposed to give input and start it, but once you do it till it completes the task, there need not be any human intervention. It will keep on doing the task continuously, right, without any human intervention needing. Okay, so one such example I wish to show you people. One second. Like, I want to show a video that was done with a software called LabVIEW programmed application. I just want to quickly show you where a simple automation that was making a very big difference. I'm going to quickly show you. Wait a second. I'll load it. Yeah. All right. So just see this video. This is a pencil sorting video. I'll tell you what is this pencil sorting video doing. Hope you people know how a normal Nataraj pencil looks like. Nataraj pencil. All right. How it looks like? It looks like the red color with black stripes. That is how a Nataraj pencil look like. Okay. So that is how a Nataraj pencil will look like. The color pencil of Nataraj usually, the red pencil will have a red skin, plain red, no stripes or nothing. Green pencil will be plain green. Pink pencil will be plain pink. Brown will be plain brown. That is how Nataraj pencil, what we commonly people have used, especially South Indian people. We use this Nataraj, Apsara, Dukes. These are the pencils we use. This was actually a company called Hindustan Pencil was doing this application. This was done by a company called Soliton. I'll tell you what is the problem with this Hindustan pencils. This is also a color pencil, but the problem is the skin of the color pencil are all even, which means that everything doesn't have any paint on them. So your green pencil will have a wooden texture outside. Your pink pencil also will have a wooden texture. Your yellow pencil also will have a wooden texture. Only difference is the lead will be of different colors. Okay. So now there is a huge task in front of us where, after the production of hundreds and hundreds of pencils within a few hours, we are supposed to sort them color wise. Why a sorting of color wise is needed is because during the packing, a pack of 10 colors is there, let me say. So one from this, one from that, one from this, one from that, you can make a packet very quickly. So if you are segregating it, it's very easy to do the packing. So from the production to the package and distribution team, you need to go through this process of segregating the pencils, sorting them color wise. So the problem here is the colors are not painted on the skin. They are only on the lead. So when a human being is trying to hand pick them, it becomes very a difficult task, because you're supposed to look at the lead and understand what is the color and put it on the right box, right? Either it is a very tedious process, number one. Number two is more amount of effort is needed. More number of people are needed, obviously, because one person sitting and doing this for all 10 colors, it's going to be a very slow process. So you need multiple people, either one person for every color. So he's going to take care of one particular color. And on top of all these things, the chances of error probability is high. So to avoid this, there are automation needed. So automation is needed for various reasons. There's one such reason here. Just watch how it is doing. So what's happening is there is a camera fixed. So this camera will be capturing the details about the pencil on the conveyor belt. I was talking about the conveyor belt, right? So the products move on the conveyor belt. So even here you can see the product is a pencil here and the product moves on a conveyor belt. So here what is happening is the products are arranged on the conveyor belt randomly. So nobody knows what is the sequence of the pencil which is lying there. There are multiple colors. So what happens is the camera is put there to understand at what order the pencils are randomly arranged. Okay. So now what happens is there is a camera which is capturing this information. It has the information in the database, something like first is a red pencil, second is a green pencil, third is pink, fourth is once again a red, then a brown, then a black, once again a pink. It has all this information. Okay. So then what happens is this information is shared to another actuator. Whatever you see here, this is an air piston. Air piston is very similar to your air gun. You know what it does is it will shoot air. Okay, how it works is usually you people know the solenoid. Solenoid is something, but there are different types of solenoid. You know springs. I am pretty sure everyone would have come across spring type solenoid. You know, if you go to your puncture shops to refill the air inside the bladder of your tire, they used to have a pump. What they do is they put it on the nozzle. They'll push it. Once they push it, what happens is it's a spring which is inside, which opens, and a high flow of air will be moving inside your bladder and fills the air. Okay, this is spring type. Whatever you see here in the screen is a digital type. So what is digital is when you give a high pulse, it opens, the solenoid opens and the air passes out. And when you give low, it closes the wall. So what is happening is one particular air gun, one particular air piston will be targeting only one color. So you'll see that in the lane, since camera has captured all the information, that information is shared to this solenoid. So the solenoid will be knowing where the red pencils are. Okay. So you'll see that after capturing the details, this will be shooting only a red pencil. So what happens is the red pencil is flying away from the lane and gets collected on a different conveyor. You'll see whenever there is a red pencil, it will shoot the gun. You can see there are multiple guns. So this will be targeting one color. This will be targeting the color number 2. Likewise, all will be there. This is what I was trying to say. You need a human being to select all the settings. Okay, what is the pass percentage? What is the colors you want to sort? What is the defect configuration? How do you want to save the details? In what format you want to save? How much of a pencil should be sorted in a single day? All this information will be done by that person. But once he is given the command to start, the application keeps running. This is a LabVIEW program. This is a National Instrument product. The camera which you saw was a National Instrument based camera, a smart camera. All right. And the software which was used, whatever you saw, the software which was running, right? That is a LabVIEW software, which is once again a National Instrument product. So National Instrument gives you hardware and the programming software, which is called as LabVIEW. All right. So I'll close this video. So hope you people understood a glimpse of how National Instrument was using NI technology, or sorry, how was they using automation. Okay, so this is what I want to bring it to you. Now I'm just quickly jumping into Industrial Revolution 4.0. So as I told you before, 2.0 is an upgrade of 1.0. 1.0 was it was powered using steam and water. Okay, and then Industrial 2.0 was an upgrade of 1.0, where there was some mass production coming into picture, where whatever was happening in a single machine, we were trying to put it in our huge factories, and we were trying to use a lot of conveyor belts. We were trying to push the data from the DUTs, device under test or device under production. We'll try to move it from one station to another. Then Industrial Revolution 3.0, where robots came into picture, programmed applications were coming into picture. That is where first time electronics was highly used, and then computers was used. So when I say computers, softwares were coming into picture. That's why properly automation was coming into picture, semi-automation was coming into picture. Now we are going into from 3.0 into 4.0. Once again, 4.0 is nothing but it's an upgrade of 3.0. Okay, so what is that we can upgrade on this missions? That is the ultimate idea, what industries are looking out for. So ultimately, people are trying to design a cyber physical system. Okay, so we already have robots. Robots are nothing but, in a very crude way of saying, robots are a physical system. So you have a physical entity which is doing a task for you. So this task has to be converted into a highly specialized or highly specific application designers, where you can bring in some artificial intelligence to it. You can also bring some cyber physical system. Cyber physical system is nothing but which has the internet connections. So the data will be shared among themselves. So ultimately, what is the Industrial Revolution 4.0 is targeting is, so we are currently implementing the 4.0, so which means that we are not sure what is the proper standard, because everyone are trying different technology. National instruments themselves, they are doing a lot of research. They are trying to invest in a lot of tools, a lot of research works. So because a lot of traffic issues, because already we know that when the single Wi-Fi in your home or in your college or wherever it is, you see that many people, once they start connecting, your data becomes slow, right? So can we put some priority based application controls into this kind of high traffic risky networks? So we have to come up with a new networking systems. So should we use IPv4? Because addressing, when I say IPv4, the model is like 255.255.255.255. This is how our IP address looks like in this format only, right? So how many entities can get connected? So usually, to make sure they are in one network, so you should basically have them to be 1.x.x.x. Okay, so how many number of devices can connect? Is maximum can be 255 cross 255 cross 255 cross 255. This is the amount of devices you can connect, which is actually very low. You might think 255 power 4 is not that small. It's a huge number, you might think. But I would suggest, just imagine we are trying to design some smart factories. We are trying to design something like, smart cities. We were talking, a few years before, we were talking about smart cities. That is where, even Amaravati was, one of a smart city that is supposed to be as a smart city by the end of 2022. That was a promise made to us by the government, but I don't know how much we have progressed. But smart cities, when I talk about smart cities, which means that entire city has items, things which is, smartly connected, smartly working. It has artificial intelligence. This is what it basically mean by. So just think in a city, in one entire city, which has n number of colleges, n number of homes, n number of shops, n number of complex, n number of industries, n number of farmland, n number of devices used in the farmlands. All these things are connected together. Do you think 255 power 4 number of devices is sufficient enough in this entire amount of data? No, that is not possible. So we have to find out, if you want to connect more devices, then we have to go for IPv6. Till now, we people have not successfully done anything in IPv6. IPv4 we are using very comfortably. I know IPv6 is not done. So a lot of research are happening on that also. So how to prioritize, the important transfer, even that is happening. How to prioritize, what is the packet system should be used. We people use TCP/IP, right? So what happens if TCP/IP happens? How slow the data will? Packets can't be sent so slowly, right? So there are a lot of research work happening in network level also. Forget about automation level. Network level also, there are a lot of problems coming up. So people are trying to work on that. So we are not sure what is the high standard or what is the standard thing we are supposed to follow. People are coming up with a lot of research. That is where these field. So whenever you see there is one industrial revolution happening, One thing is there are a lot of job opportunities because the ultimate reason is new things come across, new technologies come across. We people, for example, let me say I have 8 years experience in industry. Now suddenly new things are coming up. Okay, I am busy in doing some projects, some some client works are going on. I can't stop my work. For me to learn a new thing, I don't know how much time I'll be having to go learn a new stuff and come back. Okay, so but when you see industry people who have more time on research, you can spend more of your time on your research. We people are more into where we are target oriented, where we are supposed to complete a project. We have deadlines. We have capital cost involved in our works, whereas that is not a huge level of capital cost involved in that. So you people have sufficient time. The amount of people you people can involve, because you have some students. So you have a group of students. You have junior faculties. You have junior research fellows. Where you can involve more people. Only problem you might be having is the facilities. Okay, the infrastructures might be the problem with you people, but workspace level wise, how much people you can involve will be totally in a different ratio compared to us in industries. So that makes you people have more time to do a lot of research works. That is the reason, if you see in the recent time, there are a lot of workshops happening so that people are trying to learn. This is a part of research. These workshops are part of a research where you people are trying to come across new steps of how industries are trying to handle. You see here, especially even in this current workshop, what we people are doing, you see there are a lot of people talking for like 1 hour, 2 hours. They're trying to share their information. So ultimately, you people, I don't know what the person spoke yesterday, what the person spoke in last session. I don't know what they are going to talk tomorrow. I don't have much idea about that. But you people who are just watching, you have more idea about what everybody does. So you have more skills to do a lot of research work. That's where what happens is new technology will be evolving, new things will be coming into picture, where new job opportunities will come into picture. Your students will be start doing new level of projects like final year projects or mini projects, or your PhD work level will be totally different, right? So that should be somewhere in the next technology level. Okay, so try to do these things. So coming back to Industrial Revolution 4.0. So the production systems that are already having computer, which means that Industrial Revolution 3.0 already had computers, robots. So these robots are now expanded using a network connection. What they are doing is they're trying to connect these devices through networks. Okay. Excuse me. They're connecting through network. So that's where this is called as a cyber physical system. So this enables devices to communicate, share the information about themselves to other devices. Excuse me. Okay. So ultimately what they're trying to say is, so when there are multiple systems in an industry, they share the information about themselves. Okay. Very simple. If you ask me why it is needed, I'll give a simple example. You see driverless car. Driverless car is fully automated. It's fully automated. So it doesn't need a driver. It will drive you in the roads. Even if it is traffic, it should be driving you in the roads. That is what it's supposed to do ultimately. In this case, what happens is, just think all the cars are driverless car. So obviously they should share the information. So one car should be knowing where the other cars are moving, right? So it should have some sensors to communicate how far it is, how close it is. So it should be knowing that the nearby car is going to take a right. We people use indicators, we people use horn to communicate with each other when you drive. But there are some other sensors in market that makes this thing more comfortable, more accurate. So these machines should be communicating themselves, right? When you're trying to design artificial intelligence system, right? So this is characterized by an application of information and communication, which means that you have your information through sensors. Information is nothing but details about that particular machine is information. What is it doing, how it is doing, what time it did what, right? How much time it will take to complete this, what is the product it is using, what is the chemical it is using. All this information will be shared and communicated with each other. So this information, when I talk about information, is nothing but that self information about a particular mission. It is usually acquired through a sensors. Okay, so the networking of all these system leads to a cyber physical system. So what happens is we have robots. Now we are going to communicate them through cyber network. That is all it is. Okay. So how to build a cyber physical system? Very simple. We already have robots. We already have flexible automation robotics are available. That is Industrial Revolution 3.0. The first point, whatever I see here in the screen, that is already available as a product of Industrial Revolution 3.0. Ultimately, you have to do two things. One is give connectivity to these robots. And number two is intelligence. Intelligence is nothing but artificial intelligence coming into picture. Okay. Why artificial intelligence is needed? So that there is no need of any humans to say what to do. Ultimately, it will know what to do. Basically, it will try to sense what is the product coming. Now, for example, very simple example is once again your now what I can say is your washing machine. You had semi-automation. Now there is fully automation. What is this fully automation doing? Very simple. See, once you load the device and just simply start power on the machine, it already knows how much product is there. How many cloths is there. It knows how much dirt is there. It knows how much water to take. It knows how much soap to use. It knows how much time to use. It knows what is the heat it should set it. It knows how many spins to make, right? So it knows everything automatically. You don't have to set anything. The input is not needed, right? The input is not needed. You have to load the item into that machine. So once you load it, no input is needed. Inputs are self-driven. That is very important. The inputs are self-derived so that the machine knows what to do itself. You don't have to specify. Industrial Revolution 3.0 was about telling what is supposed to do, right? We have to give some human commands so that machine will know what is supposed to do. But when it comes to Industrial Revolution 4.0, we don't have to do that, right? So very quickly moving into section number 2. Before that, I'll come back to, I told you, right? Before going to section number 2, I'll come back to the software demonstration to you people. All right. I want to quickly show you the demonstration of how Industrial Revolution, LabVIEW can be used. Okay. So this is a LabVIEW tool. So this is what we'll be using to program all the NI products. So national instrument products. So here, what I'm going to do is I'm going to take a, so there was somebody has raised the hand. I'll come back to the meeting. Okay. I think it's in the browser. Any queries, anyone? You can just unmute and ask me. There is a person called Siddhartha.
Who have any questions can unmute and ask.
There's some error. Yeah.
Sir, we can control this Zoom link.
Sorry, sir?
We can control only, sir.
Okay. Fine,
You can continue, sir.
No issue, sir. Okay, fine, sir. I think by mistake they have pressed it. I don't know, maybe.
Okay, okay.
Okay. What I'll do is I'll take a new VI. VI is a place where we'll design the application. I'll take a blank VI so that I'm going to quickly show you how these applications are designed. Okay. See, what I'll do is I'll tile them side by side so you can see both the screens. There are two screens now in front of you. One is a front panel, one other is a block diagram. Okay, so I'll just slightly bring it down so you can see the names also. So one is a front panel, the other one is a block diagram. I'll quickly give introduction to this window so that I'm going to do all the code development in this window only, right? So first of all, I'll make you clear that front panel is a place where the user interface will take place. User interface is nothing but you go to ATM machine, where you specify the inputs to the machine and the machine will try to interact with you. It interface the user's inputs with the machine. Okay, so it will ask you, how much money you want, what is your PIN number, type the PIN number. It will ask you, do you want to print the the details or other things, print the balance, do you want to display the balance, all these things will be asking. So this is going to be the place where the UI will take place, which means that the front level of window, the front window where you people can see and work on that. Okay. Block diagram is a place the actual code will run. Block diagram is a place where your actual programming will take place. All right. So now I'm going to quickly show you a simple addition of two numbers, for example. So to do addition of two numbers, what we need is we need two inputs, one output. Right? I repeat, I'm going to simply show you how addition program can be done with this LabVIEW tool. So you'll understand the environment. That's the reason. Okay. So just watch here. When I right click on the front panel, you have a palette called as controls palette. And when I right click on the block diagram, you have a palette called as a functions palette. Controls palette, functions palette. Okay. So if you want to design anything on the front panel, you have to use the controls palette. If you want to design anything on the block diagram, you have to use a functions palette. Very simple. Just right click, you get a palette and drag and drop items from that particular palette. So I need addition of two numbers. When I say numbers, it's a numerical data type. So you can see that once I right click, you can see all the items are classified or put into a folder based on their data types. Boolean, numeric, string, graphs. Okay, so these are all classified based on their data types. Okay, so what I'll do is I'll go to numeric. In LabVIEW, controls are inputs, indicators are outputs. Okay, so your inputs are called as controls and outputs are called as indicators. So we need two inputs and one output. In other words, I can say we need two controls and one indicator. So what I'll do is I'll go to numeric. There is control here, there is indicator here.
Hello, sir.
Yes, sir.
Sir, sorry to interrupt. I just one message to the participant. You can unmute yourself and you can ask your questions. We give you the access. You can unmute yourself and you can ask your question.
So this is Siddhartha, sir. Sorry, sir. Previously, I just raised the hands up because I am query.
Okay, now if you have any question, any doubt, you can
I was unable to
yourself.
unmute, sir, previously. Sir, one small question, sir.
Yes, sir. Please, sir.
Yeah. So you told like previously that with respect to machines communication.
Yes, sir.
So means how the machines will communicate and all, sir.
Yes, sir.
In the previous presentation.
Yes, sir.
So in that one, sir, say for example, machine 1 and machine 2, machine 3 are present, sir.
Yes, sir.
Now, due to some issues and all, machine 1 is not working properly.
Yeah, yeah.
So in that case, again, a machine 1 has to build its all software and again getting back its original positions and all. Means after repairing it, it has to come back to its original position.
Okay.
So in that case, the data what is present in machine 1 means from the beginning 18, it has to communicate it to machine 2 and machine 3, sir.
Yes, sir. See, I'll tell you how this basically environment work. Anyway, I was supposed to tell you next. I'll tell you now, no issues. Just see, always these missions will go, no, see, as I told you, these are all, there are multiple stations. I'll talk about stations. You talk missions, I'll talk stations. So a product goes through station 1, then station 2, then station 3. Okay, in this, what happens is if station 1 is dead, so the product that is supposed to go into station 2 will not happen. The station 2 product should go to station 3 will not happen. Okay, so the entire line will be dead if station number 2 or station number 1 is dead. So now what happens is people don't want this to happen. So what they do is we have something called as life monitoring or health monitoring for every mission, first of all. Okay, so what happens here is, so you will understand the product or there is some spare parts available. The spare part, for example, let me say your phone also. Your phone will come up with the battery life monitoring, right? Something like that. Even nowadays, AC, Daikin AC. There is a company called Daikin. These company ACs, they come along with health monitoring system. What happens is it will keep on monitoring the spare parts health information and keeps on sharing to a main master computer where maintenance is taken care. Okay, so here what happens is anywhere you feel like there is a degradation, not shutdown, where there is a degradation happening, it means that there is all possibility for a machine to shut down. All right, in that case, what happens is all the information will be quickly taken back up. Okay, all the data, all the products, because once it is not dead, right, we don't know whether it will switch on. The products information internally will be somewhere dying. That's why what happens is they'll transfer all this information to a substitute mission, or they'll take a backup or before this shutdown, they try to do the maintenance. This is how people are handling products. There is a shutdown or something happening. This is what people are trying to currently do. That's what we people are doing currently. There is no much idea about how we people can handle this. Only thing we are doing is missions condition monitoring is what we are doing. Missions health monitoring, missions lifetime monitoring. These are the three things we basically do. Three things are totally different. Condition monitoring is different, health monitoring is different, lifetime monitoring is different. So these are three things we are basically doing to understand whether a mission goes to shutdown. Because once it shuts down, there is nothing we can do. We have to wait for the maintenance system to come and make it better. Then the communication happens. So there is nothing we can do once the mission is shut down. One thing we can do is we can ensure the mission will not shut down, or we'll predict when the mission will shut down. That is why, based on some algorithms, we'll understand the health monitoring, we'll classify or we'll predict the future of the health monitoring of the mission. Okay. Clear, sir? Did I answer your question?
Yes, sir. One more query, sir.
Yes, sir.
You're telling, you just now told like lifetime monitoring will be there, no, sir?
Yes, sir.
So if suppose any machine has been designed, then what is means how much lifetime period will be having any kind of a machine?
So usually when one machine is produced, let me say a company called Bosch is designing a machine, sir. Okay, a common product they are coming in the market. So they will give a certification saying that this is the lifetime of the machine. Okay, so what happens is under that they'll have some warranty. Under that they'll have some servicing. Everything will be there. I think you know this. When you buy anything, you'll have a warranty, right? So based on that, a machine life will be decided. So usually when it comes to industries, people will not be happy to buy anything or any product which is having a lifetime which is less than 7 to 10 years. Okay, 5 years also depending upon what type of product they'll allow, but there is a long run or continuous things happening, then people will not be ready in industry level. They don't want to do the servicing nearly for 7 to 10 years. So if the product is designed in such a way that it will break down, or the lifetime of this product is only 1 year, there is no point in investing on that product, right? So usually the term life will be usually 7 years, sir. Term life will be usually 7 years. So between that, calibrations might be needed. See, every year there is a calibration needed, people can understand. But lifetime is only 1 year or 2 years. That is not the right thing. Minimum will be 7 years. I also know there is a machine from Bosch which has 25 years of lifetime. Okay, they guarantee that this machine will not break down for 25 years. So these kind of products with high quality comes with G, Snyder, and Allen's. There is a company, PLC designing company called Allen's. So they also give high quality. Then even your Bosch gives high quality. So these are the companies that gives high quality products where the lifetime is very huge. So usually, the term life will be 7 years minimum. Clear, sir?
Yes, sir. Thank you, sir.
You're welcome, sir. You're welcome. Okay. So coming back to this window, this is a front panel. So I'm going to right click numeric. I'm going to drag and drop controls. I need 2 controls and 1 indicator. Just watch. I'll drag and drop control. I can name it as input 1 or A, anything, my wish, my variable name. We name it as A, B, X, Y, something like that. We name it, right? This variable name, input variable name, I'm naming it as A. I'll drag and drop one more. I'm going to name it as B. 2 inputs are created. 1 output is needed. Output is nothing but an indicator. I'll drag and drop this. I can name it as C. Here, look here, you can design it however you want. You can increase the size. If you wish to change the colors, okay, you can change the colors. Let me say I want all to be a red color. So I can do all these changes. How you can design however you wanted the front panel to be. There is no much designing on the block diagram because it's a code which is running. This is a graphical code which is going to run. So there is no much designing needed here, but this needs perfect designing. So you can resize, you can go for any type of font. You can see what type of font you want. You can pakka design however you want it. Okay. So after designing 2 inputs and 1 output, I'm coming to the block diagram. So here what I'm supposed to do is I have 2 inputs for whatever I created inputs and outputs. There is a terminal here on the block diagram. Okay. So I'll right click on the block diagram. I need an operator now. So I go to numeric. Then I see, you can see that if I need to do some numerical operations, I go for numeric. And I have all the operators or arithmetic items which is related to numeric inside. If I say Boolean, I have all Boolean items. If I say string, all string items. If I say array, there will be all array items. Okay. So I go for, numeric. I'll take an add function because I want to add these two inputs. I'll drag and drop it like this. After finishing this, very simple, just touch this, click, and connect it here. We people have used MS Paint, right? MS Paint. It's more similar to that. Draw a line like this. If you wish to remove some wire, click on that, delete. If you want it back, Control Z. If you want to select all, you can draw a wire like this, delete, or you can press Control A and you can delete however you want, right? So deleting the items are very simple. See, just see, click on it. You can see that I'm clicking on it. It is selected. I'll delete. Okay, Control Z will come back. Fine. I'll provide some data here, some random numbers I'll just put here. And if I want to execute this code, I'm supposed to come here. There is a run button at the top. In the toolbar, this is a toolbar. So you have a run button. Right? So what happens is when I click on the run button, I've not clicked it. When I click on the run button, this value of 34 will move to this window. This terminal will pass a value of 34 here. And this value of 67 will move here. And this will be passing a 67. The output, I mean, the inputs will be added and the output will be pushed here and the output will be shown here. So ultimately what happens is you don't want to see what is happening on the block diagram. People are more interested in what is happening on the front panel only. Okay. So when I run this program, you'll see the output is available. No one knows what is happening in the behind. This is a developer screen. I'm doing a development here. So you will be able to see both the screens. But once you complete the product, you share the exe file or an installer file. In those cases, a block diagram will not be displayed to them. Okay. So right now, this is a development window I'm designing where you can see both the screens. But once you complete the product or complete the application, complete the software, you share an exe file, not the source code. This is called as a source code. You won't be sharing the source code. You'll be sharing only the exe file. The exe file will have only the front panel. It will not have the block diagram shown to them. All right. Only the source code will show the block diagram. Okay. So now if I just give some fractional data or a negative data also, right? It should, oh, sorry, minus 9.4. Right? So make it a little bigger so we can see the numbers, all the decimals, right? So if I run this, you can see the update. But what I want is, as soon as I change the value here, I want a spontaneous update here. For this, I'll use the second button called as run continuous. So here you can see any changes I do, whatever I type here, it will immediately update. Can you see? Yes. If I want to stop it, I'll click on this or click on this abort button. It will stop immediately. Clear. This is a graphical programming language where we don't use syntax. So what is the syntax? Syntax is nothing but see, when you use a C program, right? In C, what we do is we'll start with hash include std.h, hash include conio.h. Then you just specify the inputs, then you specify the outputs. Then you go for the operation C equal to A plus B. Okay. Then what you do is you want to print it, or you want to you go for get ch and then you close the application. Right? Whereas here it is very simple that you concentrate only on the C equal to A plus B. We don't include all this hash include and other things. Not only in LabVIEW, I'm not specifically talking about LabVIEW. Any graphical programming language, when you see a ladder logic is a graphical programming language. You see PLC ladder logic. If you have heard about it, you will know that even that uses what is that graphical programming language where we don't much involve syntax. Okay, there are a lot of circuit designing softwares now coming across where they're allowing you to drag and drop what component you want, and you just simply connect them and your output works, right? So there are like virtual instruments are available, like front panel of CRO or function generators is available, so you can just quickly give the data and that you can use it for your circuit as an input, and the output will be seen once again in an oscilloscope. Those things are also quickly possible. So there are a lot of software based Hello. Hello. Any doubts, anyone?
No, sir, you can continue.
Okay, sir. Thank you. So This is a graphical programming language where the syntax will not be involved. All right. So quickly jumping into the artificial intelligence, deep learning and machine learning. I'm going to show a demonstration on a deep learning.
Hello, sir.
Yes, sir.
You're telling like there is no syntax in this graphical programming language.
Yes, sir.
If suppose after generating the entire design, if suppose I would like to generate the C code or else any other programs like syntax.
From this one, you want to generate the C code, is it?
Is it possible, sir?
Not possible, sir. That is not possible. But one thing is possible is we have VHDL. I don't know whether you people are aware of VHDL. You people are from EC department, am I right? Yes, so sir. FPGA programming for Xilinx embedded programs. There, if you see, you have Verilog program and you have HDL program, VHDL program. Okay. So there, what you can do is at the end of the day, it will generate a bit file. That bit file will be deployed into your FPGA chip. Okay. Likewise, LabVIEW can also be used. At the end of the day, you can choose what kind of bit file you want to generate. That is the only thing you can do is, but from here, generating a C program or generating a Python program or assembly language program is not possible. Okay, sir. This is a parallel thing which is similar to them. So we don't generate any codes from here. That is not possible. Fine. Thank you, sir. Okay, sir. Fine, sir. So I'm quickly jumping into the machine learning and deep learning. So you'll see that.
Excuse me, sir.
Yes, sir.
So you said that we can generate the bit files, sir. So those bit files can be directly synthesized to the FPGA board, sir, the Spartan 6 or Zinc FPGAs.
Right now, only Xilinx FPGAs can get deployed with LabVIEW programs. Sir. Right now, see, National Instrument and Xilinx together have a handshake, and not all chips also. So there are limited chips we have. So what happens is only the limited chips you can program using LabVIEW. Xilinx is providing something like you can program it either using Verilog or VHDL or LabVIEW. They are giving that feature. Okay. Not all chips can be done, like Spartan chips. I'm not sure. It's not possible, I think so, sir.
Okay, okay, sir. Okay, sir. Thank you, sir.
Yes, welcome, sir. Okay, so coming back to your machine learning, I'll go for a toolkit called as now right click. We use numeric, right? Like that, we have much more signal processing. If you want to use, you can use all the functions here. Okay, so if you want image processing, then you go for this palette and you have a lot of image processing stuff. Okay. So you'll see that a lot of applications related to count measurements, contour analysis, all these things related to image processing is available. Okay. Likewise, if you're interested for image processing based machine learning or deep learning, image processing based machine learning, deep learning, if you want to do, go for vision and motion, machine vision, you have machine learning. Inside that, you have deep learning if you want. So these toolkits have to be installed. You have to install it. Excuse me. So now let me say your application is not image processing oriented machine learning algorithm or deep learning algorithm. It's a common numerical or signal processing based classification or prediction. Then what you have to do is you have to install a software called as add-on toolkits. Inside that you can see machine learning, right? So you have unsupervised version, all algorithms, supervised all algorithms you can see. Okay, this is for machine learning. And if you want it for deep learning, there is a company called Nijin, and Nijins basically provide you the deep learning algorithm toolkit for LabVIEW. Okay, so inside this you can see all the applications related to your deep learning is available. So you have to drag and drop them, like how we dragged and drop your add function, something like that. You have to drag and drop this. All right. So I have made one simple code for you people. I'll show that code. That was basically based on supervised technique of machine learning. So I don't know how much time will be there. So I just made a small Excel sheet. So I'm just opening the Excel sheet. So this is a pulse prediction, heart pulse prediction, heartbeat in other ways. I can also say that heartbeat prediction using KNN algorithm. KNN stands for K nearest neighbor. Okay, K nearest neighbor algorithm I have used. Of course, all these things. So just see here, I have two classifications. This is a classification method where I have two conditions. One is a 0, which is a normal condition. One is an abnormal condition. Okay, So you can see that any value around 78, 75, 74, 73, 70, I have classified manually as, normal condition. And even here, you see there are a couple of normal condition values. And let me say there are some low values like 65, 66, high value like 85, 90. They are classified as abnormal. Irrespective to, low or high, it is all abnormal. Okay. So this is a set of data I have already made, right? This is a training set of training data. Okay. So based on this, I'm going to predict using KNN algorithm. That's very important. KNN algorithm is what we are going to use. And this is a simple application I've done. Okay. So any values beyond this values which is given from 78 to, so for example, let me say starting from 65 or 60, I think. Randomly few numbers are missing here. From 60 to hardly 90, I think, 94, I think. Okay, there are some randomly scattered numbers classified as, normal and abnormal. So now randomly when there is a value, a pulse rate is measured. Let me say 87, 55. Okay, randomly some number is coming. It should predict and tell me whether it's abnormal or normal, right? So this prediction system I'm going to quickly do. So heart pulse measurement. All right, this code I'll just quickly explain what is it happening. So you can see that I've loaded LabVIEW. Can also load your Excel sheet information into LabVIEW. Okay, so you can see this function name is read delimited spreadsheet. So right click, file IO on the block diagram. I'm on the block diagram. You can see the name is block diagram. Right click, I'll go for file IO. There you have write spreadsheet, read spreadsheet. Excel sheet. Spreadsheet is the Excel sheet. Okay. So here I've just loaded this particular data which is saved in my computer. Okay. So I saved in my computer. It will read and give you all the data here. So when I run this program, forget about these things because right now it is not used. I have not given any value. Forget about this. You can see it has loaded all the data from the Excel sheet. It has loaded all the data from the Excel sheet. Now, based on these data, I'm going to classify. Now, let me say there is a number which is not here. For example, one number, I'll take it. 63 is not here. For example, I'll go with the number 63. There is no fraction number, basically. I'll go with the fraction number. Usually, your pulse is not fraction number, but I want to use a number which is not in this list. So I'm using a fraction number because none of the numbers are fractional, right? So I'm going to take 63.12. Sorry, 63.12. Okay, I've taken a number, right? So I want to, apply the KNN algorithm on this set of data and predict this number is a abnormal or normal condition I want to predict. This is what I'm going to do. Okay. So when I run this program, I'm not run the program. When I run the program, it has executed and it is saying that the predicted label is 0 or 1 we have, predicted label is 1, which means it is abnormal. Okay. I'll go with some number like, 72.65. There is no 72.65 here. So when I run it, you'll see that it has substituted this value using KNN algorithm into this data set. And it's now predicted as, normal BP. Okay. So how I've done, very simple, what I've done is I've extracted only this particular list of data. This data and this data, I've extracted it here. So from the array of information, whatever you see here is a 2D array. From the 2D array, the data what is in the Excel sheet is converted into 2D array of string data. From there, I've extracted the data. Okay, I extracted the information here. Okay, this is nothing but is your values data, and this is nothing but is your data labels. That's 0 and 1. Then I provided to KNN algorithm the same thing. So the same thing I've used. Both are same. So KNN algorithm, where I get it from, very simple. I'll go for add-ons, machine learning, supervised technique. KNN falls under supervised technique. You can see KNN algorithm. Okay. So what is this KNN algorithm doing? Okay, it's very simple. What it does is now you're supposed to specify what is a K value. KNN, right? K stands for a constant value which you specify. I specified here the K value is to be K equal to 3. So what it does is for the specified input, new sample, it will take 3 nearest neighbor, that is called 3NN. So here in this, it will check what is the nearest neighbor. Why I go for 3 is, I won't go for 2 or I won't go for 4. The reason is, sometimes it happens when you go for even number, 2 comes in this category, 2 comes in this category. So once again, you are not sure how to predict it. So this is a prediction where I'm going to say it is 2, or sorry, 3 or 5. I can go for 5 also. Here, if I say an odd number, there is a conclusive data like one side is 3, one side is 2. All right. But very importantly, you'll see that, usually go with the odd number, and this n value should be more than the number of labels. That is the condition, because now let me say there are 5 data here, 5 labels here. There are 2 labels, 0 and 1 only. Now let me say there are 5 labels and you're giving 5 and n. So what happens is, by chance, who knows, there are 5 labels classified. Every label has 1 member. So first label has 1 vote, second label has 1 vote, third label has 1 vote, fourth label has 1 vote, fifth label has 1 vote. Once again, you will not be able to predict it. So in that case, if the number of labels are 5, go with a value called 7. Okay, go with a value called 7. Even then, you can see that sometimes it will not be more accurate. Okay, it will not be more accurate. Can you people mute it? Hello. Thank you so much. Okay, so always go with the odd number and make sure the number is more than the labels. The k value should be more than the label. Clear? And this is a simple mathematical application. I was talking to you all about image processing based machine learning, right? Image processing based machine learning or deep learning. I have made a video. There is a video with how LabVIEW works. Yeah, this is a deep learning based classification. This was done with LabVIEW. You can see here, this is a LabVIEW program. Okay, the same LabVIEW program. Symbol you can see, it's a LabVIEW program. You can see these are all LabVIEW functions. They are classifying the different. You can see here the labels are different. Here the nuts are the labels. You can see that in real time application, video processing, where image processing is also involved, because LabVIEW's image processing involves video processing also. You can see the others are also there, which is not classified items. You can see here. Yes. Yes. And also there is this is signal processing based. This is signal processing based. Now this is a handwritten you have, OCR, optical character recognition. You hear about it. This is more similar to that, but this is using a deep learning algorithm, not OCR technique. So you can see that you can write any number on the screen and will predict what number is that. Okay, so we were till now seeing how deep learning, machine learning based algorithms can be done. I want to also show you what happens when IoT is involved to these applications. That's what I wanted to show you. For that, I have a video to play for you. Just watch this video. I want you to watch this video. It shows if AI is powered with IoT. Okay, if AI is powered with IoT, what kind of applications can be designed is going to be demonstrated here. It's slightly a bigger video. It's like 5 minutes video. Just watch this. It's very effective. This basically gives you the idea about what kind of applications, what kind of research activities, what kind of products can be based or can be developed. Okay, so you can see that it's a cloud-based automation.
चाउमीन, आलू पराठा, पुलाव, फ्राइड राइस। चाउमीन, आलू के पराठे। हाँ, गरम खाना, आलू पराठा। अच्छा, खाना लगेगा सर? नॉन वेज?
You can see here one simple example of how things can work with artificial intelligence. Just see here, the lawn has already sensed there are some people occupied. So at 5 o'clock there should be a lawn sprinkling. The water has to be done for the grasses. So it understands there are 5 p.m. and there is no rain. So you have to water it. So lawn is occupied. So delay it it will snooze for 5 minutes. Just see.
चाउमीन है, पुलाव है, बिरयानी है, फ्राइड राइस है, खाना है।
Yeah. So we're trying to show you if the AI system is interfaced with your IoT, so you can make sure all the things can be far done better. That was a demonstration video, but the idea was so cool. I think someone is unmuted. Can you people mute it? Hello. So I think someone is unmuted. Please, everyone, check your mute. Leave yourself muted so that I can now do the session without any disturbance. Okay. Hello. Okay. Fine. Now what I'm going to do is I'm just going to quickly come back to your slides where I'm going to quickly introduce you about the IoT also. So when I talk about IoT, this is where I was telling you people about the IPv4 and IPv6 comparison also. Something like that. Further more comparisons I'm going to bring to you. So the difference between Internet of People and Internet of Things, I'll first bring it into your communication. What is the difference communication and how they will have. So we people use internet for various purposes, for chatting, sending images, sending videos, sending mails, scan copies, attach any of the documents. Right? You have multiple information, live streaming. Our live class is also going. Live streaming is also happening now. So these are the different informations we share. These are all related to our activities, right? So the things wise, when it comes to Internet of Things, this is Internet of People, what you see in the screen. When it comes to Internet of Things, the items what they'll share will be totally different. Okay, so when it comes to Internet of Things, there will be n number of items, n number of gadgets will be transferring the items from one place to another, from one machine to another. I'll take a very simple example. For example, you have a wooden piece. You want to paint it, then dry it, okay, and inspect it. Okay. So once painting is over, it has to be dried. After drying, it has to be inspection should be taken place. Okay. So in these kind of activities, right? What are the information that will be shared is what is the paint color, what is the paint level, whether the product is a good product or not, whether it is passed or not. Okay. So what is the height, what is the thickness of the wood piece, all this information will be there. And based on this information, the oven will be setting the time, setting the temperature, and it will not make sure that extra resources being used, and will make sure the proper even thing. Can you people just mute it? Hello? Someone has unmuted it. Hello? Thank you so much. So what I was trying to say is Internet of Things, right? Yeah. In those cases, what happens is the machines will be communicating their own informations. Okay. See, for example, I'll just tell you, when it wants to send the information related to particular object, right? So there should be a sensing device. There should also be a communication device, right? Because when I say the information what we share is totally different from the information what the machine shares, the machine gets its information from the sensors. Okay. So you need sensor and communication medium so that your things will change into a IoT things. Okay. When you want Internet of Things, what you do is you have already the existing items, existing robots you have. For that, you have to add the sense and communication. So we people have 5 sense organs, right? We people have 5 sense organs, but I could say we are limited to 5 sense organs. Whereas when it comes to the non-living things, there are a lot of sensors available. What are the different types of sensors available, right? See, for example, few examples I can give you is we people don't know the location where we are living in. Now, let me say I'm stuck in a room. There is no light here to see which direction the light is coming from to see the sun. I don't know it is morning or night, right? But if you have a phone, this phone knows the GPS location, correct? The phone can communicate with the satellite and understand the GPS location, whereas which is not possible for a human being to find out. So when we are lost, we try to take a help of a phone to understand where we are basically. That is how Google Map also works, right? So we are, having some good sense organs which, machines don't have. For example, smell, we have gas sensor where it finds whether there is a smoke in the place, but we don't understand, for example, we people know what is the classification of the smell, whereas there is no specific sensor which can find the variation of the smell using a sensor. That is not possible right now. It is not possible. There's a lot of research happening in that, but even now there are some sensors, high quality sensors are there, but they are also in research level. But even the level of difference they can find is very minimal, whereas we people can have huge level of smell, variation, understanding, and ability. Forget about we people. There are dogs, there are cats. They have even higher sensing thing naturally, but still there is a disadvantage. There is advantage also. But right now we have. When I talk about in the previous, the thing also I was trying to show you. So when a thing has sense and communication ability, I repeat, just watch it, this is very important. When a non-living thing or when some instrument, when it has a sense and communication ability, it turns into IoT device. Okay, so coming back again here, one such example is your phone. Your phone has multiple sensors. It knows GPS location. It knows what is the temperature. It has weather report also, right? So it knows what is the temperature around it. It knows what is the light. It knows how close I'm holding, near my ear or far away from it. It knows what acceleration I'm just holding it. There are a lot of sensors inside, and it can also communicate. It has internet, right? It has, it can make calls. It can send some SMS. So it can also communicate with other devices. So one such example of IoT device we already have is phone. One more device I can give an example is your smart wristwatches, where it measures a lot of items like it measures your heartbeat, it measures your number of steps you have taken in a day, how much calories you have burned, whether you slept properly night or not, right? And it can also communicate to one more device like a phone or like some main database wherever you're holding all your health report, or to a doctor it can send the information. There are also wristwatches like that. So this is also an IoT device. There is a thermostat. This is not famous in India, but in some European countries, you will see that there are thermostat where it understands how many people are in the room, what is the temperature, should I switch on or switch off the heater or the cooler. It has all the information related to that. So how to bring in fresh air. So whether a fresh air is needed right now, or it is sufficient enough to have this, this level of thing. If you burn something inside the room, it will understand there is a toxic gas there. So the exhaust has to be switched on. All this information will control. The entire, weather, climate inside the room will be controlled using this thermostat. Once again, this will communicate through internet again. You also have Alexa nowadays. It controls all the home appliances with voice control, right? Something like that. This is also something similar to that, but this is not voice control. This is artificial intelligence system, sensor based. Your laptop is also one such IoT device. Only it has a lot of sensors. It can connect to a lot of sensors externally also, because you have RS-232 port. There are a lot of sensors nowadays coming with protocol based sensors. These sensors can communicate the device information to your laptop. Laptop can communicate to Wi-Fi, or it can communicate to any other medium. So laptop can also be converted into IoT device, I'm trying to say. All right, fine. So how an IoT individual device will look like? I'm talking about an IoT individual device. So an individual device will have n number of sensors and should also have a control unit to process it. What I mean by control unit to process it, it should take decision. IoT device, right? It should take, AI should be empowered. So it should take decision. To take decision, it needs a processor to do it. So when there is a processor, along comes a battery usually. See, for example, I'll talk about my laptop, my phone, or my, the wristwatch, smartwatches. Whatever you come across, they always need charge. You've seen this. See, for example, I'll talk about my phone. My phone, I charge twice in a day. I don't know about you people. The only IoT device, for example, let me say I have one IoT device I charge twice in a day. All right. Just think in the future, all the devices in your home is IoT device. If you're supposed to charge it twice a day, all the devices, how many power sockets you need, how much electricity you need. It's going to be a complicated thing. That is where many companies are now coming across battery management system. Okay, battery management system is a huge upcoming industry that many people are not really aware of it, because your vehicles also now, hybrid vehicles are coming across, electric vehicles coming across. People, petrol rate is like rising like anything. People want everything to be renewable energies, right? There is smart grid, lot of research happening in smart grid, microgrid, right? Power transmission analysis. So what is the reason is because the power badly needed for most of the devices in the future, right? So that's the reason battery management systems are huge or a very blooming research area. All right. So after that, you need a communication medium. Very simple, right? So you need sensors, a processing unit, and then a communication medium. These are the things you need. So based on the size of the communication medium, your IoT device can be classified into 3 types. Okay, IoT network can be classified into 3 types. So it can be a personal IoT. Personal IoT is PIoT. Okay, or you have commercial IoT, or you have industrial IoT. Industrial IoT is what IIoT is. Okay, so personal IoT is something, but if I use a communication medium like a Zigbee or a Bluetooth, and I communicate my phone with my headphone with my wristwatch with my mouse, laptop mouse, very small congested area where I communicate only my own personal devices, which is all within a range of my 5 to 6 feet around me. Then I'll use a network called as personal area network, PAN. Okay, personal area network. That is called as personal IoT. Then comes a commercial IoT, where commercial IoT is nothing but it is more similar to that, but the range is pretty high. Let me say I have one building. Inside one building, all the devices should be communicating. I can use a Wi-Fi where I want to connect my projector, I want to connect my printer, I want to connect my laptop, I want to connect other instruments, whatever I have, right? So all these devices, I communicate with each other. I can use a Wi-Fi. That is called commercial IoT. Then come industrial IoT, where the data should communicate from one place to anywhere. It can be a city level, it can be a country level, it can be a state level, it can be global level also, right? So that is wide area network. You have PAN, you have LAN. LAN, if a IoT device used a LAN communication medium, then it is called as commercial IoT. If a IoT device used a PAN, then it is called as a personal IoT. A communication medium, IoT device, if it has a WAN, wide area network, then it will be called as a industrial IoT. Okay, these are 3 differences you have to come across. Different types of IoT based on the network range. Very important, network range. Okay, and then comes the other classification, like depending upon the network's capability, you can classify into active cloud and passive cloud. There are a lot of other things. I'm not getting very depth into it. What I'm trying to say is, when you're trying to design it, choose your proper network. So what size, how many devices you have to connect. Based on the number of devices, you have to choose whether you want to go for IPv4 address or IPv6 address. Right now, we are going to show simple demonstration with couple of computers where we can go for IPv4 only. All right. So what I'll do is I'll quickly come for a demo to you people. So what I'll do is I'll first come for cloud designing. So to do this cloud designing, what I'm going to do is I'll take a new tab. Okay, I'll take a new tab. I'm going to type Firebase. So Firebase is the platform I'm going to use to program using LabVIEW, send and receive the data into the cloud. Okay, so I'm first designing the platform. Just watch out. So I'll go for Firebase. This is a Google platform. So Google is giving a free. There is also paid version of the same Firebase where you have more access and credentials for this. But for simple data transfer and real-time database, you can use a normal free Firebase version. I'm going to show you how data communicate from one machine to another. I'm going to quickly show you. Okay, I'm going to design and show you because I think I have nearly 20 to 25 minutes of time. So I have more time to show demonstration to you. So what I'm going to do is I'm going to get started. All right. So I'll create a project. I'm supposed to give a name to it. I'm going to name it as okay. I'm supposed to give a name. It can be same name. It is giving me this suggestion. I'll go with my project 123. I'll go. Okay. Any name is fine. I'm just going with my project 123. I'm creating a project. All right. It says these are the features you have, because I told you there is also another version of paid version. Right now we are not using that. So it says what are the access you have. It is asking me to choose. This is a default account. For this account, whatever credential you have, okay, those are the available analytics you can possibly do. So it will ask you to choose which account you want, and I'll say create project. It's pretty simple. People can try in your laptop also if you have. So you can see that it is creating the project. This is the platform it is first creating. This is where your IoT cloud is getting created. So usually you'll notice that once it completes, I'll show you. You'll notice that when you're trying to do this, you need to log in into your Gmail account, because as I told you, this is basically from a Google platform, right? So once it's done, it is asking me to continue. My project 123 is completed. Okay, you can see that it is logged into my Google account, right? So the reason why your Google login is needed is you're going to send some data and you're going to save or store for particular amount of time, temporary amount of time, because your data from your machine 1 is going to the cloud, and from the cloud it is going to the machine number 2. There can be no time difference between this, so the data has to be temporarily stored into the cloud. Google right now has not allocated any memory unit to store all this IoT device data. So what they're doing is, what Google has now decided to do is, for your Gmail, they give 15 GB of data for your Gmail, right? So that is where all your Gmail will be saved. Your Google Mail will be there. So once you log in, this memory of 15 GB now will be utilized to save the data. If you ask me, is 15 GB is sufficient enough, you have to plan it accordingly, right? Whenever you want to clear it after using it, once you push the data into the machine number 1, from machine number 1, if it is received in all the other missions where it's supposed to be received, you have to properly handle it and delete it, right? Or you have to use a paid service where there is a high level of data transfer allowed to you. All right. So I have logged into my account. You should first log in and then create a project. Okay. First log in and then create a project. Okay. Now what I'm going to use, these are the different types of service they provide to you. Here under the build, you can see authentication, Firestore database, real-time database. So I'm going to use something called as real-time database. Why it is called as a real-time database? On real-time, I'm going to send and receive the data from multiple missions, right? So I'll go for real-time database. Okay, so click on real-time database and say create database. So now it is asking what service provider you wanted to prefer. See, depending upon where the location of the user is, Google has classified to 3 different types. So since we are from Asia, we are supposed to use the base or the database provider of Singapore. Okay, it works for all. Even if you give United States, it will work. But just to make sure to reduce the traffic level, they have given 3 different databases. So try to prefer that so that we will avoid traffic as much as we can. Okay, I'll say next. So here there are 2 modes, test mode and lock mode. It can be anything is fine. The reason is I have to change it anyway. Even if I choose this, I'll change the rule set. Even if it is like this, I'll change the rule set. Next step is going to be changing the rule set. Just watch. Okay, so it can be any method, test mode or lock mode. You'll see that it is anyway created. Can you see here? This is the platform, cloud platform is created. This is where all the data are going to be saved. This is the console where all the data are going to be saved. Okay, so first of all, what I'll do is the data are here, the rules are here. I'll come to the rules tab. As I told you, right, it doesn't matter it is, what method it is. Okay, so I'm gonna make sure both are gonna be true. I think my T button is not working. Okay, so I'll type true. Okay, even here I'll choose true. I think my T button, my laptop is not working. Okay, so you can see the rules: read equal to true, write equal to true, right? So I'm changing that and I'm just gonna say publish. You can see the rule sets are published, right? And after setting the rules, I come back to the data, right? So here, this is the project you have. There is nothing under this project, which means that, see, every project can have n number of child. Child is nothing but it's going to be the variable which is holding your data. Okay, so I want data to be hold. So I'm going to name it as random. Okay, the variable name, the child name, where under this all the data are going to be saved. So it can be something like IR data, depending upon what information it is, IR data. Okay, so it can be RFID data. Okay, it can be anything. Okay, I'm going to name it as random data or normally data. Name it as a random, and the value is nothing but the data type you want it to be holding. So I'm going to use double quotation like this. Okay, so there's some issue with this laptop. Okay, so I'll open and close a double quotation like this. Okay, so open close double quotation means it's a string data type. Why reason? You can ask me, why are you preferring string type? Because when I'm saying random, let me say I'm going to push a number. It is supposed to be configured to be a number, numerical data type, right? But I'm just configuring to be a string data type. The reason is we're using a HTTP protocol here. So here this console itself is using HTTP protocol. It's a hypertext protocol, right? So it's a textual program is what, in a textual data is what is going to push using this data type. I mean this communication protocol. So what I have to do is I have to convert all the data into a string data and push it here. Okay, I have to push it here. So I'm going to name it and give the data type and say add. Right. So you can see under this there is a child name random. I have multiple, like I'm going to name it as IR, and once again the data type you are supposed to specify. Okay, so I'll specify the data type and click add. You can have a number of childs under this. Okay, so it is nothing but one mission's data, mission number 1 data. It can send n number of parameters. Okay, it can send n number of parameters here. All right, now let me say I'm supposed to write the data into this particular parameter. Okay, so when I click on that, you can see that under this project, now we are inside the random. When you want to come out, click on this. If I click on IR, you can see it is inside IR. So all the data will be stored here. Okay, so I'm just going to go for random. Can you see this is the hyperlink you have? Can you see the hyperlink at the top? Okay, what I'll do is I'll copy, Control C, copy. Yes, madam. Any queries, anyone? Okay, so I'll copy this because this is what we are going to need. I'll come to LabVIEW and I'm going to quickly show you how to program this. Okay, I'm going to quickly show how to program this. I'm going to go for string constant and I'll first paste this data. I'm taking this information and I'm pasting it here. That link. Okay, so and then I'm going to name it as .json. JSON is nothing but it is the type of string what we are going to use. JSON, JSON. So I'm giving the extension as .json. This is the extension or the type of string data we are going to use. Now we have to use a protocol, HTTP protocol, and push the data into the cloud. I'm going to show you how to push it into the cloud. Data communication, data communication protocol, HTTP protocol, right? This is the protocol we are going to use. I'm going to show you again in the block diagram. We used, the add-on functions and all I showed you, numeric function I showed you, something like that. Data communication protocol, HTTP protocol. So I'll drag and drop open. Open is gonna create a memory to do this task. So we are going to push the data into the cloud. That is the task we have now. So this opens the memory for that. Then you need to put the data. So I'll use a function called as put. Visible item, label, put. And then finishing that, you have to kill the memory. Since you created a memory, you are supposed to kill the memory. So once you have completed it, you can kill the memory. All right. Then I'll connect them in sequence, because why I'm connecting in sequence like this is, it has to happen in sequence only, right? So first you have to create a memory, then put the data, then close it, right? So I'm just putting them in sequence and connecting them through wires. So they'll execute in sequence. All right. So here there is an option to mention your URL. There's an option to mention your URL. This URL is nothing but your location in your HTTP internet where the cloud is already existing. Okay. So here I'm just passing the URL. And then you have the buffer. Buffer is nothing but your data. So this is a real-time database where you continuously write the data. So it is named as buffer. Okay. So then I want this to happen continuously. I'll take a while loop. A loop, loop will do the task continuously. I'm keeping only this part inside the while loop. The reason is memory will be created once. This particular task will execute multiple times, and this will kill the memory once. Okay. So this is the condition for the while loop, and I'll control the speed of the while loop. I'm going to say I want to push the data once in every second. I want to push once in every second, or every 1 second I want to push one data into the cloud, right? So it's a real-time database, right? So you have to specify how fast, how quick the data has to be sent into the memory of your cloud. So I'm just specifying it to be one data per second. One data per second. So 1000 is nothing but in millisecond. So 1000 millisecond is equal to 1 second. So while providing 1000 millisecond, it means that it is 1 second only. This means 1 second of delay, so that this put will always execute once in every second. I'm controlling the speed of the data to be transferred. Then I don't have a sensor here. If there is a sensor like temperature or health monitoring sensor or humidity sensor, whatever may be the sensor, I can connect the sensor data, push the data here. I don't have any sensor currently here, so I'm going to use a random number generator. So this is going to generate a number between 0 and 1, a random number generator. This is a simulation. I'm simulating the sensor data by using a random number generator. This data I'm supposed to push into the cloud. Okay, this data I'm supposed to push into the cloud. Okay, to do this, the problem here is if I directly connect this data here, it will not happen. It is throwing error because here it is a string data needed. I told you when you use HTTP, you have to use string only, but this is not going to happen. So what I'm going to do is I'm going to go for string palette, flatten unflatten string, to JSON, and from JSON I'm going to use. But here I'm going to use to JSON because from numerical data, from numerical data, I'm going to convert it into a string and I'm going to send it like this. The problem you will face here is this will not directly connect to this. It will throw error. The reason is you are sending a real-time data, which means it's a plural, multiple data have to be sent. You are sending a single data, which will not happen. So in this case, what you have to do is again, I'll take array, insert into array, insert this data. What I'm doing is a feedback. Feedback, right, everyone? So output is provided here. So what happens is first it starts with an empty array. So create constant. So it starts with an empty array. Can you see the array is empty, nothing inside. empty array. Okay, so to the empty array, one data will be included, and the output will once again come back. One more data will be included. The output will come back. This is insert into array. I think it might look slightly complex because you're new to this toolkit, maybe because of that, but it's pretty simple compared to other programming language. So what I'm doing is this data, the output which comes, I'm parallelly always writing. So this process is also happening. This process is nothing but inserting new element into the array continuously inside the loop. Okay, and that data parallelly I'm writing it to the cloud also. Okay, so if I want to see this, I'll right click here, create indicator. There's no responding here. I'll right click here, create indicator. Okay, so I'll be seeing what is happening in the LabVIEW level also, and we'll cross check whether the same data is pushed into the cloud or not. Okay, so what happens is every 1 second, one new data will get added into this array. First citation, one number between 0 and 1, because random number generator, this function generates a number between 0 and 1 only. That is the ability of this function. Okay, I'll tell you the information about this. This produces a double position floating point number between 0 and 1. Okay, so this random, very random. We don't even know. We can't even predict what number is going to come. The random number will get generated, and it will be put into the array, and that information is passed into the cloud again and again. Okay, so now what I'll do is I'll minimize all these things. I'll keep this parallelly visible to you, so both windows are available. Very importantly, I'm writing into the random. Can you see inside the Firebase? Random is the child I'm using to send the data. So I'm coming into the random child window, and I'm just leaving this to be visible to all, so you people can see here. I'll run this program. It will initialize first because it has to create a memory. I told you, right? Create a memory, and it will start pushing the data into the cloud. Can you see here? The data has started pushed into the cloud, right? So ultimately what happens is when I stop here, the data push also will stop here. And this information, this is the industrial IoT standard application where I'm pushing the data into the internet. If anyone who has this link, the link is nothing but this link. Okay, anyone who has this link can push the data into the cloud. You understanding what I'm saying? Anyone who has this link can push the data into the cloud. Okay. Okay. So if you want to see it in this platform, you need my login also. Right? So without this login, pushing the data from LabVIEW to this platform is possible. But if you want to see this data in this platform, then you need my login also. I repeat, to push this data into the cloud, anyone in this world need this link. But if you want to see the data, you need my login also, because I am pushing into my login credential. So it is all said in my login credential. Pushing the data only needs the link, but to view the data in the cloud level, you need this login of my mail ID also. Okay, now I have done the first half. Data is being pushed into the cloud, right? Data is pushed into the cloud. I'm going to show you how to call it back again, because from mission 1, the data is put into the cloud. From cloud to mission 2, it has to go, right? So that I'm going to show you, right? The same application. One thing is I'll copy this link because I need the link. I told you to read the information. Once again, you need the link. Okay, this link, I'll paste it here. This link is needed. This time, I think it will be pretty easier. The reason is we already saw how I was doing the previous time. So once again, data communication, protocol, HTTP client. I'll pin it. I'm going to use multiple items from here. Once again, I'll open the memory. When I open the memory, I should close it. So I'll use close memory also. Close, fine. Then before I use put, now I'm going to use get. Put is to put the data into the cloud. Get is to get the data from the cloud. So I'll give a label to this so you can see. Same way, I'll connect it here to here, here to here. All right, I'll just align them so that it looks neat. Okay, so then I have the URL to be specified. URL is nothing but this link is the URL. So from this URL, it is going to fetch the data to you. I'll close this, is not needed anymore. So then I'm going to use a while loop. Why while loop? Because I want to continuously again and again read the data. Okay, because it's a real-time application, right? You're going to continuously write it. So we are using a loop. Same way, if you know the speed of the data to be sent into the cloud, then you can use this, or it will wait infinitely. Let me say if you're going to execute it for every 10 millisecond, there you're pushing the cloud to the cloud at every 1000 millisecond, but here you're trying to read it every 10 millisecond. Then what happens is the data will be read again and again. Same iterative data will get, but I will just give it 1000 because I know at what speed the data is being transferred. Okay, so the output comes from here as a body. Can you see? There is also a header, there is also a body. Body is what the actual data is. Header is nothing but your actual cloud's information is a header. I want the body, all the entire information. It comes in string. So I'll go to string palette, flatten. Before I use to JSON, now I'm going to use from JSON. So drag and drop this. So this body to my JSON string, and to what data type it's supposed to be converted. Here there is an array of numeric, right? I'll copy this, I'll paste it here. This is just to say from numeric it will convert into this data type what you specify here. This is a reference, so this data should be converted into this referred data type. So the output will be numerical array indicator. Can you see here? Numerical array indicator. So slightly increases size to its visible to you all. Okay, so I'll resize the window size also so that people can see all screens together. Okay, this is send data. I mean, Untitled 2 is sending the data to the cloud. So I'll slightly make this also small. Yeah. So just watch out. When I run this program, you can see new data are being written, right? The new data are writing to the cloud. Okay. Just watch out. New data are being written. You can compare it. Here only 6 digits I'm showing. Actually, there are more digits here. I'm not displaying all digits. Okay, if I wish, I can do the setting changes and make all digits to be visible. 5.023, 5.023, 442272, 44227. 18 is now rounded off to 72. So all data are now coming here. This need not be in this machine. For demonstration, I'm using this machine. But if you have this link anywhere in this world, you can access this information. I repeat, if you have this link anywhere in this world, that is called as IIoT, industrial IoT. I told you, right? PAN, LAN, WAN. PAN is nothing but personal area network. LAN is local area network, that is commercial IoT. Then comes, your industrial IoT, which is WAN, wide area network. So when I click here, new data are being written. It is erasing all. And I click here, you'll see that data from the cloud will be received. I'll just show one more thing. I'll run only this. So new data are achieved. I'm not running this at all. Like 6 to 7 data are being written here, right? Now, even if I close it, I don't want this. I'll close this. I'll close this. I don't even want this. Okay. Even if I close this, the data are stored in the cloud. Even if I kill this machine's data, this was one person was asking me, if this machine is now corrupted, whether the data will be transferred. Yes, it will be happening. I'm just going to show you. I'll kill this code. Okay. I'm killing this code. By closing this without saving, we'll kill this code. It is killed. But the data are saved in the cloud still. Okay. This is the previous run data. Okay, when I run this, you'll see that the data are received. If I change some value, if I say 1, 2, 3 here, okay, it is not allowing me to change it here. So from the software, it's supposed to be changed. So you can see that I can delete some. Okay, I've deleted one data. So when I run it here, that will be updated here. Getting it? Yes. So this is how you'll push the data into the cloud and receive it from the cloud. It is IIoT method, not personal IoT or commercial IoT. It's IIoT, industrial IoT method. Okay. So any queries? It's already 1 o'clock. Any queries? Any queries, anyone?
So if anyone having any queries, you can ask. Anyone you want to ask, you can unmute yourself. So anyone?
With this, I'm concluding my session. I'll wait here for 5 to 10 minutes to clarify your queries if there is any. This is my contact details. You can feel free to reach me later also in case of any queries related to any technology and any other stuffs. Okay, this is a very short 2 hours duration where I have to show you all the things. But yes, there are a lot of things. It's actually possible. I was trying to show you everything at the earliest, as much as I can. Where I covered, AI, machine learning, deep learning, then how Industrial Revolution 4.0 has evolved. What are the new things? Battery management system, why it is grooming. I was telling you all about these things. Then I showed how IoT is influencing AI. I showed a video also to you people, and I showed a live demo of how to create a platform of IoT, send the data from LabVIEW and receive it from LabVIEW. LabVIEW is nothing but it's a toolkit from National Instrument to do industrial programming, right? So this is the revision of what I did this 2 hours. Any queries, anyone? I'll be happy to handle the queries if there is any.
Okay, if you have no query, we will stop the session. So let us thank Basant for his valuable talk. So
Thank you.
So on behalf of whole organizing committee, I thank you. I'm going to thank you, sir.
You're welcome. You're always welcome.
For accepting our invitation and delivering a wonderful talk. So we stop here. Thank you very much, sir. We will get back to you.
Thank you, everyone. Have a nice day. Thank you all. See you.
So here I am going to stop the session. Please join at 2 o'clock again for the next keynote speech. Okay, thank you all.